Listen, deep in the silence of space, a soundless scream erupts. In less than the blink of an eye, a wave of pure energy, traveling for billions of years, punches through the cosmos. It's a flash of radio waves so powerful it outshines entire galaxies, and then, just as suddenly as it appeared, it's gone. This isn't science fiction. This is a fast radio burst, or FRB, one of the most violent and bewildering phenomena ever detected in our universe. For a single millisecond, something out there unleashes more energy than our sun will produce in 80 years, and we have almost no idea what that something is. Imagine a cosmic detective story where the clues are these fleeting, impossibly bright signals, and the crime scene is the entire universe. That is the mystery we are about to step into. For over a decade now, since the very first one was discovered quite by accident in archived data from 2007, these bursts have defied every simple explanation. They arrive from the darkest voids between galaxies, from the deep past, carrying secrets about the fabric of space itself. Are they the death cries of collapsing stars, messages from unimaginably advanced civilizations, or the signature of exotic celestial objects we haven't even begun to theorize about? Each new detection seems to raise more questions than it answers, challenging our most fundamental understanding of physics and our place in the cosmos. This isn't just an academic curiosity, it's a front-row seat to one of the greatest scientific puzzles of our time, a real-time exploration that reminds us how much we still have to learn. Today, we embark on a journey to unravel this enigma. We are going to explore 50 distinct mysteries of fast radio bursts. We will dive into the strange repeating signals that come from a single point in the sky, the bizarre frequencies that hint at unimaginable magnetic fields, and the lonely bursts that seem to come from nowhere at all. This is a voyage through cosmic detective work, where every clue is a piece of a puzzle spanning billions of light years. So prepare to have everything you thought you knew about the universe challenged as we count down 50 mysteries that are reshaping our view of reality itself. Our story begins not with a dramatic observation in real time, but with a quiet, meticulous search through old data. It was 2007, and astronomer Duncan Lorimer had given his student David Narkevic a seemingly routine task: to analyze archival recordings from the Parkes radio telescope in Australia, searching for signs of distant pulsars. These recordings, taken 6 years earlier, were like a library of cosmic noise, but buried within that static was something that should not have been there. As Narkevic sifted through the data, he stumbled upon a signal so bizarre, so outrageously powerful, that it defied all known categories. It was a burst of radio waves that lasted a mere 5 milliseconds, but in that infinitesimal blink, it released as much energy as the sun does over a full month. They named it the Lorimer burst, and it shattered the quiet certainty of radio astronomy. The initial reaction from the wider scientific community was not excitement, but profound skepticism. A signal this strong, appearing just once, immediately raised red flags. Had they detected a glitch in the telescope's electronics, a passing airplane or satellite creating interference? Perhaps it was even a prank. The idea that a natural cosmic event could be so brief and so immensely energetic was at the time almost heretical. There was simply no known object in the universe that could produce such a flash. For years, the Lorimer burst remained an anomaly, an unsolved puzzle that many tried to explain away as something mundane, but the data was stubborn. One of the most crucial clues was its dispersion measure. As the burst traveled across the universe, its lower frequencies arrived at the telescope slightly later than its higher frequencies, a telltale sign that it had passed through a vast amount of ionized gas or plasma. The amount of this dispersion was immense, far greater than anything that could originate within our own Milky Way galaxy. This single measurement pointed to an origin billions of light years away, far beyond our galactic borders. This meant the burst wasn't just a local oddity, it was a message from the deep cosmos. The implications were staggering. For a signal to travel such an immense distance and still register as the brightest radio event ever observed, the source must have been cataclysmically powerful. Yet it left no afterglow, no residual signal, no trace whatsoever. It was a cosmic flashbulb popping once and then vanishing into eternal darkness. The Lorimer burst single-handedly opened an entirely new field of astronomy, one focused on these transient, millisecond phenomena. It was the first clue in a detective story spanning the entire universe, a signal that whispered of unknown forces and violent events occurring in the darkest, most distant reaches of space. This one-off event set the stage for everything that was to follow, proving that the universe was capable of surprises far stranger than we had ever dared to imagine. Yet for all its compelling evidence, the Lorimer burst was just one signal. In the world of science, a single anomaly can always be dismissed as a fluke, a piece of faulty equipment, or even a mistake. And so, the real mystery began not with the discovery itself, but with the agonizing wait for a second one. For years, astronomers scanned the skies, hoping to catch another of these cosmic flashes. But instead of clarity, the next chapter of the FRB story only delivered more confusion, plunging the entire field into a debate that questioned the very nature of what they were detecting. Were these bursts truly cosmic, or were they something much, much closer to home? This was the central question, and the suspects were numerous. The extreme brevity and immense power of the signal made it a perfect candidate for human-made interference. Could it be a secret military experiment, a radar pulse from a passing satellite, or some other form of terrestrial technology creating a signal so powerful it mimicked a cosmic event? The skepticism was not just healthy scientific caution, it was a necessary part of the process. Radio observatories are incredibly sensitive instruments, and they are constantly bombarded with signals from our own planet. Isolating a genuine cosmic whisper from the roar of human activity is one of astronomy's greatest challenges. The situation became even more perplexing when other telescopes started detecting similar, but crucially different millisecond bursts. Some of these signals seemed to originate from the atmosphere itself, and they bore a strange resemblance to the FRBs that had everyone so excited. The plot thickened dramatically with the discovery of what astronomers dubbed peritons. These were bursts that looked at first glance almost identical to fast radio bursts. They had the same short duration, the same intense power, but they had one telltale difference: they were coming from right here on Earth. For a time, it seemed the entire FRB phenomenon might be explained away as some kind of local interference. The mystery had turned into a full-blown cosmic whodunit, and the prime suspect was humanity itself. The breakthrough in solving this particular puzzle was almost comically mundane. After years of detective work, astronomers at the Parkes telescope discovered the source of the peritons. It wasn't a top-secret weapon or a complex satellite. It was the observatory's microwave oven. When staff members opened the oven door before the timer had fully finished, it would emit a brief, powerful radio pulse that the incredibly sensitive telescope would pick up. This seemingly silly explanation was actually a major victory for science. It proved that the methods used to distinguish local noise from cosmic signals were working. By identifying the peritons as terrestrial, astronomers could confidently remove them from the data, strengthening the case that the real FRBs were something entirely different. So how can scientists be so sure that the genuine fast radio bursts are not from Earth? The single most important piece of evidence is that dispersion measure we mentioned earlier. Think of it like this: when light passes through a prism, it spreads out into a rainbow because different colors or frequencies of light travel at slightly different speeds. Something similar happens to radio waves as they journey through the thin soup of charged particles or plasma that fills the space between galaxies. The lower frequency waves get slowed down just a tiny bit more than the higher frequency waves. The farther a signal travels through this intergalactic plasma, the more spread out it becomes. The dispersion measure is essentially a meter that reads how much intergalactic material the signal has passed through. For the genuine FRBs, this measure is astronomically high. It indicates a journey not of thousands of light years within our own galaxy, but of billions of light years across the vast, empty voids between galaxies. No earthly signal, no matter how powerful, could possibly mimic this effect. It is the indelible stamp of a cosmic traveler. Furthermore, the verification process is incredibly rigorous. When a potential FRB is detected, teams of astronomers cross-check the signal with other telescopes around the world almost instantly. They analyze the direction it came from. If multiple, widely separated telescopes see the same burst coming from the same point in the sky, it effectively rules out a local source which would appear to come from different directions for different observers. This process of triangulation and independent confirmation has become the gold standard. Over time, with dozens upon dozens of these bursts detected by multiple observatories, the evidence has become overwhelming. Fast radio bursts are not messages from our own technology. They are the faint, millisecond-long echoes of some of the most violent and enigmatic events occurring in the farthest reaches of the universe. The question is no longer if they are cosmic, but what out there is powerful enough to create them. Just when astronomers thought they had a handle on the mystery, believing these bursts to be solitary, self-destructing events, the universe delivered its greatest curveball yet. The fundamental assumption had been that whatever produced an FRB was annihilated in the process, a single, final, glorious act of cosmic violence. That simple, elegant idea was completely upended in 2016 with a discovery that sent shockwaves through the astrophysics community. A team using the massive Arecibo radio telescope in Puerto Rico found something that should not have been possible, a fast radio burst that did not die. They detected not one but several bursts, all emanating from the exact same point in the sky. This object was given the decidedly unglamorous name FRB 121102, but its behavior was anything but ordinary. It was a repeater. The significance of this cannot be overstated. Finding a repeating source was like a detective finding a witness to a crime who wasn't just present for a single moment, but who kept returning to the scene, offering new clues each time. Instead of a flashbulb that pops and is gone forever, this was a lighthouse whose powerful beam would periodically sweep past our tiny planet. This single observation immediately split the entire field of FRB research into two distinct camps. We now had two families of bursts, the one-off events, which likely were the result of truly catastrophic, single-use explosions, and the repeaters, which pointed to a source that could survive its own immense outburst and do it again and again and again. This simple distinction suggested that there might not be one single answer to the FRB mystery, but perhaps two or even more completely different physical engines powering these incredible flashes. This classification was a game-changer. For the one-off bursts, the list of potential culprits had to be objects or events that are destroyed in the process. Think of a neutron star collapsing into a black hole, or two incredibly dense objects like asteroids made of solid iron smashing into each other. These are final, irreversible acts. But for a repeater like 121102, the source had to be something far more resilient. Something that could build up and release colossal amounts of energy repeatedly without tearing itself completely apart. This pointed towards objects with unimaginably strong magnetic fields, like magnetars, a type of neutron star with a magnetic field 1,000 trillion times stronger than Earth's. Perhaps these objects experience starquakes on their solid crusts, or have eruptions in their magnetospheres that can happen over and over. The repeater forced scientists to think about engines that could be turned on and off, rather than just explosives that detonate once. But the true revolution brought by the repeater was the gift of time. With a one-off burst, you get one fleeting chance to observe it. By the time other telescopes around the world, or even in space, can swing into action to look for afterglows or other wavelengths of light, the event is already ancient history. It's a flash in the pan, leaving behind only a rapidly fading memory. A repeater, however, is a persistent target. Knowing its location in the sky meant astronomers could point the world's most powerful optical, infrared, and X-ray telescopes directly at its home and stare. They could monitor it continuously, waiting for the next burst, ready to capture its full electromagnetic signature. This ability to conduct long-term surveillance on a single FRB source was the key that would finally begin to unlock the deepest secrets of these cosmic enigmas, leading to a pinpointing of its location that was as precise as it was shocking. And with the discovery of a repeater, the hunt was truly on. For the first time, astronomers had a target they could revisit. But knowing a signal came from a general patch of sky was one thing. Finding its exact cosmic address was another entirely. The challenge was one of precision. A single radio dish, like the one at Parkes or Arecibo, can detect a burst's incredible power, but it's like trying to pinpoint a single firefly's location while looking through a drinking straw. The field of view is simply too wide to isolate the specific galaxy, let alone the specific object within that galaxy responsible for the flash. To solve this, astronomers needed a much sharper eye, a way to zoom in with unprecedented clarity. The breakthrough came not from building one bigger telescope, but from linking many smaller ones together in a technique known as interferometry. This method is a stroke of genius in modern astronomy. By combining the signals from multiple radio dishes spread across a vast area, scientists can effectively create a virtual telescope as wide as the entire distance between them. It's like creating a giant cosmic magnifying glass. Two key instruments led this charge. In Australia, the Australian Square Kilometre Array Pathfinder, or ASCAP, uses 36 identical dishes working in concert. When a fast radio burst flashes through its field of view, a tiny, minuscule difference in the time it takes the signal to reach each individual dish allows a supercomputer to calculate the burst's position with astonishing accuracy down to just a few arcseconds. To put that in perspective, that's like spotting a coin from a distance of over 30 miles. Meanwhile, in the high desert of New Mexico, the Very Large Array, a legendary setup of 27 massive radio antennas, was also turned toward the mystery. The process is a breathtaking race against time. When one of these arrays detects a burst, an alert is automatically sent out to observatories around the world within mere seconds. This triggers a coordinated global effort. Optical telescopes like the Gemini Observatory in Hawaii and Chile, or even the Hubble Space Telescope orbiting high above Earth's atmosphere, immediately swing into action. They abandon their scheduled observations and slew or turn to focus on the precise coordinates provided by the radio array. Their mission is to stare at that tiny point of sky and answer the most pressing question: what is there? The first major success in this high-stakes localization game was the repeater itself, FRB 121102. When the VLA turned its collective gaze toward its location, it didn't just detect more repeating bursts, it pinpointed them to a faint smudge of a galaxy more than 3 billion light-years away. This was the moment the abstract phenomenon became a tangible reality. We weren't just detecting mysterious signals, we were now looking at the very neighborhoods where they were being born. The host galaxy for 121102 was a surprise. It wasn't a grand spiral like our Milky Way or a massive elliptical galaxy. It was a tiny, puny dwarf galaxy, far smaller and less substantial than our own. This was a crucial clue. It suggested that the conditions necessary to produce these immense bursts might be more common in smaller, more chaotic stellar environments, where star formation is rapid and violent. This process of localization is far more than just placing a dot on a map. It is the fundamental first step in forensic cosmic science. Identifying the host galaxy immediately gives astronomers a treasure trove of information. They can measure its distance, confirming the dispersion measure estimate and solidifying the burst's immense power. They can study the galaxy's composition, its rate of star formation, and the types of stars living within it. It allows them to ask critical questions. Is the FRB source located in a dense star cluster near the galactic center or out in the lonely outskirts? Each piece of environmental data is a potential clue to the engine behind the burst. For the first time, instead of just theorizing about what could cause an FRB, scientists could look directly at where it does happen, narrowing down the list of suspects from the infinite possibilities of the cosmos to the specific conditions of a single, identifiable galaxy. This precise localization transformed the mystery from a philosophical puzzle into a solvable scientific investigation. This process of pinpointing the homes of these bursts revealed something astronomers did not expect: a host galaxy enigma. The assumption might have been that something so powerful must come from the biggest, brightest, most massive galaxies in the universe. But the cosmos, as it so often does, defied our expectations. Instead of a single type of galactic neighborhood, FRBs are turning up in a startlingly diverse range of cosmic environments. It's as if we've been tracking a series of incredible explosions and found they are happening in everything from gigantic, sprawling metropolises to tiny, remote villages. On one end of the spectrum, we have the host of the famous repeater, FRB 121102, a faint dwarf galaxy. This is a small, chaotic place, rich with gas and furiously forming new stars. In such a nursery, massive stars live fast and die young, exploding as supernova and leaving behind dense remnants like neutron stars. This environment seems like a perfect breeding ground for a type of neutron star called a magnetar, which is a leading candidate for producing these bursts. The logic is compelling. A young magnetar born from a recent supernova could be surrounded by a dense cloud of debris. Powerful flares from this highly magnetic star could then interact with that cloud, producing the intense radio flashes we detect. A dwarf galaxy, with its frantic pace of stellar birth and death, fits this picture beautifully. But then, other localized FRBs were found to originate in massive, quiet, and evolved spiral galaxies, much like our own Milky Way. These are older, more sedate environments where the era of frantic star formation is largely over. The stellar population here is older, and the massive stars that could birth young magnetars are long gone. So what could be causing FRBs in these peaceful galactic giants? The answer might lie in a different kind of cosmic violence, the slow, gravitational dance of stellar corpses. In an older galaxy, the most likely progenitors could be the mergers of incredibly dense objects, like two neutron stars spiraling into each other or a neutron star colliding with a black hole. These are one-time, cataclysmic events that would perfectly explain the non-repeating FRBs. This diversity suggests a profound possibility that the term fast radio burst might not describe a single type of event, but rather a final, common signal produced by several completely different cosmic processes. The plot thickened even further with a discovery that truly upended the playing field: FRB 2020-00120E. This repeating burst was localized with incredible precision, not just to a galaxy, but to a very specific and ancient place within it, a globular cluster in the nearby galaxy M81. Globular clusters are dense spherical swarms of hundreds of thousands of stars, and they are among the oldest structures in the universe. The stars in this cluster are billions of years old. This finding was a major shock to the field. How could an environment devoid of young, massive stars, the very factories that create magnetars, host a repeating FRB source? It forcefully challenged the idea that all repeating FRBs are linked to young, active magnetars. This forced theorists to think outside the box. Perhaps in these ancient stellar cities, magnetars can be formed through alternative, slower channels. One intriguing possibility involves the evolution of binary star systems. In the tight confines of a globular cluster, a white dwarf, the aged remnant of a sun-like star, could be pulled onto a neutron star by intense gravity. The accumulation of this material could cause the neutron star to spin up rapidly and gain an immense magnetic field, effectively resurrecting it as a magnetar late in its life. Another idea posits the collision of two white dwarfs, creating a magnetic neutron star through a pathway that doesn't require a recent supernova. The existence of FRB 2020-00-120e is a powerful reminder that the universe is more creative than our theories. It tells us that the conditions for creating these mysterious bursts might be far more varied and ubiquitous than we ever imagined, occurring not just in the fiery cradles of young stars but also in the quiet, ancient graveyards of the cosmos. But to truly grasp why these signals are so baffling, we need to move beyond their distant origins and confront the sheer, staggering scale of their power. This brings us to the sixth and perhaps most fundamental mystery, the prodigious energy problem. What does it mean for a burst to outshine entire galaxies? Let's put some numbers to this cosmic violence. A typical fast radio burst, one that lasts just a few milliseconds, releases an amount of energy in radio waves that is almost beyond human comprehension. We're talking about the equivalent of 500 million suns shining with all their might, but only for that fleeting instant. To frame it in a more personal timescale, in the literal blink of an eye, a single FRB can emit more energy than our own sun will radiate across every single wavelength over the next 80 years. This isn't just powerful, it's an energy density that defies our understanding of physics. Now, there's an important nuance here that makes this even more extreme. When astronomers calculate this energy, they often refer to the isotropic equivalent. This is a critical concept. It assumes the energy is blasted out equally in all directions, like a perfectly spherical explosion. Think of a light bulb that shines with the same intensity in every direction. If an FRB were truly isotropic, its total energy output would be almost unimaginably large. But in reality, the emission is almost certainly beamed, focused into a narrow jet like a lighthouse beam rather than a bare bulb. We are only seeing the fraction of the energy that happens to be pointed directly at us. The incredible implication is that the total energy involved might be significantly lower than the isotropic equivalent, but the local energy density, the intensity within that narrow beam, must be even more extreme to appear so bright from billions of light years away. So whether the total energy is truly astronomical or just intensely focused, the underlying physics required is equally extraordinary. This immense power, released in a mere thousandth of a second, places incredibly tight constraints on the source itself. The first and most basic constraint is size. Nothing can travel faster than light, not even information. This means that for the entire emitting region to flash in unison, to appear as a single, coherent burst to our telescopes, the entire source cannot be larger than the distance light can travel in that millisecond. That distance is about 300 kilometers, roughly the distance from New York City to Boston. So, whatever is creating this galaxy-shaking flash must be smaller than a modest-sized asteroid. We are looking for an engine that fits within a volume smaller than many cities, yet can, for a fleeting moment, outshine hundreds of millions of stars. This immediately rules out entire classes of astronomical objects. It cannot be a supernova whose explosion unfolds over weeks and involves a star much larger than our Sun. It cannot be the merger of two giant stars. The source must be incredibly compact and incredibly efficient. This combination of tiny size and unbelievable power rules out nearly every conventional power source we know. Chemical energy, like the burning of rocket fuel, is laughably inadequate. Even the intense energy released by nuclear fusion, the process that powers stars, falls short by a factor of billions. The only known forces in the universe that can conceivably operate on this scale are gravity and magnetism. This is why theories immediately point to the most extreme objects known, neutron stars and black holes. These are objects where matter is crushed to densities where a teaspoonful would weigh billions of tons, and where magnetic fields can be 1,000 trillion times stronger than anything we can generate on Earth. In such an environment, a sudden rearrangement of the magnetic field, a starquake on the solid crust of a neutron star, or the rapid accretion of matter onto a black hole could, in theory, liberate the required energy. But even these extreme scenarios are pushed to their absolute limits. A magnetar flare, for instance, is one of the most violent events we know of in our galaxy. But the brightest FRBs we detect from across the universe appear to be hundreds or even thousands of times more energetic. We are forced to ask, are we seeing a known type of event operating at its absolute maximum, or are we witnessing an entirely new class of phenomenon, one that harnesses physics we have not yet discovered? The prodigious energy problem is not just a detail. It is the central challenge that every successful theory of fast radio bursts must ultimately solve. This mind-boggling energy output, however, is only half of the equation. The other half is the breathtaking speed at which it all happens. The defining feature of a fast radio burst is not just its power, but its brevity. These are cosmic fireflies, flashing into existence and vanishing again in the time it takes a hummingbird to flap its wings once. We are talking about events that are typically over in 1 to 5 milliseconds. To put that into a human context, a single blink of your eye takes about 300 to 400 milliseconds. An FRB unfolds and concludes in less than 1% of that time. This incredibly short duration is not a trivial detail. It is one of the most critical clues we have, placing a severe and unbreakable constraint on the size of the object responsible. The logic behind this constraint is rooted in one of the most fundamental rules of the universe. Nothing can travel faster than light. This principle of causality means that information cannot propagate instantaneously. For an entire object to appear to flash on and off in perfect unison from our distant vantage point, the signal to erupt must have traveled across the entire source region in a time shorter than the duration of the burst itself. If the object were too large, we would see a time delay across its surface. The outer edges would light up later than the parts facing us, and the burst would appear smeared out in time, not as a sharp, crisp spike. The fact that the burst is so sharp and short tells us that the entire emitting region must be smaller than the distance a beam of light can travel in that single millisecond. So, what is that distance? Light, the fastest thing in the cosmos, travels at about 300,000 kilometers per second. In 1,000th of a second, light covers a distance of 300 kilometers. That's roughly the distance from Washington, D.C. to New York City. This simple calculation delivers a stunning conclusion. The cosmic engine capable of outshining galaxies must be crammed into a volume smaller than a modest-sized asteroid. We are searching for something with the power of a supernova condensed into a space no larger than a city. This immediately eliminates vast categories of astronomical objects. It cannot be a regular star, which are typically millions of kilometers wide. It cannot be the explosive death of a large star, a supernova, which unfolds over days or weeks as a massive stellar envelope is blown apart. The source must be inherently compact, a celestial object where immense mass and energy are packed into an incredibly tiny space. This narrows the list of suspects dramatically, pointing the finger directly at the most extreme and bizarre denizens of the cosmic zoo, compact objects. These are the leftover cores of dead stars where matter has been crushed to unimaginable densities by the force of gravity. The prime candidates are neutron stars, black holes, and white dwarfs. A neutron star, for instance, is the collapsed core of a giant star that went supernova. It packs more mass than our Sun into a sphere only about 20 kilometers across, easily fitting within our 300-kilometer limit. A white dwarf, the remnant of a smaller star like our Sun, is Earth-sized but contains a sun's worth of mass. Even the event horizon of a stellar mass black hole is only a few kilometers across. All of these objects are, by their very nature, compact enough to be the source of a millisecond burst, but being small enough is only the first step. The real mystery is what physical process on or around such an object can release such colossal energy so quickly. Gravity alone isn't fast enough. The slow, stately inspiral of two objects takes thousands of years. The answer must lie in processes that involve the sudden release of stored energy, like a cosmic spring uncoiling in an instant. For neutron stars, especially the highly magnetic variety known as magnetars, two leading mechanisms fit the bill perfectly. The first is magnetic reconnection. Imagine the magnetic field around a magnetar as a tangle of immensely powerful, twisted rubber bands. These fields can become so stressed that they suddenly snap and reconfigure themselves into a lower energy state. This reconnection event converts immense magnetic energy into heat, radiation, and particle acceleration in a violent flash that can easily occur on a millisecond timescale. The second mechanism is a starquake. Neutron stars are thought to have a solid, incredibly dense crust surrounding a superfluid core. As the star spins down over time or experiences a sudden shift in its magnetic field, this crust can fracture, much like the tectonic plates on Earth. But a starquake on a neutron star is nothing like an earthquake. The energy released is titanic, as the entire crust, which is 1 billion times stronger than steel, shifts by just a few centimeters. This sudden movement releases gravitational and elastic energy, shaking the star's magnetic field and potentially triggering a massive flare. Both magnetic reconnection and starquakes are cataclysmic events that operate on the required stopwatch timetable, providing a plausible physical link between a compact object and the fleeting brilliance of an FRB. The millisecond timescale, therefore, is far more than a simple measurement. It is the key that unlocks the door to the type of engine we are searching for, forcing us to look at the most dynamic and violent processes occurring on the smallest, densest objects in the universe. So if the engine must be incredibly compact and capable of releasing staggering energy in a millisecond flash, what natural object fits the bill? The current leading contender in this cosmic investigation is one of the most extreme and terrifying objects known to science, the magnetar. To understand a magnetar, you first need to picture a neutron star. When a massive star dies in a supernova, its core can collapse under its own gravity, crushing protons and electrons together to form a sphere of neutrons so dense that a single sugar cube-sized piece of it would weigh as much as a mountain. A neutron star is a city-sized object with the mass of our Sun. Now, take that already bizarre concept and amplify it to an almost absurd degree. A magnetar is a neutron star that, during its violent birth, was spun up to an incredible rate and developed a magnetic field of almost unimaginable strength. The numbers involved are truly difficult to grasp. The Earth's magnetic field is what makes a compass needle point north. It's strong enough to protect us from solar radiation. A typical neutron star has a magnetic field about 1 trillion times stronger than Earth's, but a magnetar, its magnetic field is another 1,000 times stronger still, 1,000 trillion times more powerful than our planet's. This creates an environment so extreme that the physics itself becomes distorted. The magnetic field of a magnetar is so potent that if one were located halfway between the Earth and the Moon, it would effortlessly strip the information from every credit card on the planet. In this realm, atoms are stretched into long, thin needles, and the vacuum of space itself is polarized. It is a crucible of fundamental forces operating at their absolute limit. The connection to fast radio bursts comes from how these monsters release their pent-up energy. Magnetars are not quiet, stable objects. They are seething with stress as their unimaginably powerful magnetic fields are constantly twisting and straining against the star's solid, ultra-dense crust. This leads to two primary mechanisms for colossal outbursts. The first is a starquake. As the magnetar spins down over time, its crust, a material 10 billion times stronger than steel, can suddenly fracture. This isn't a gentle tremor, it's a catastrophic event where the crust shifts by just a few centimeters, but in doing so, releases more energy than our sun emits in 100,000 years. This sudden release shakes the star's magnetic field, triggering an immense flare. The second mechanism is magnetic reconnection. Think of the magnetic field lines around the star as giant, twisted rubber bands storing immense energy. When these field lines become too tangled, they can snap and violently reconnect, converting that stored magnetic energy directly into radiation and a blast of particles in a process that unfolds in milliseconds. Both of these phenomena, starquakes and magnetic reconnection, are perfect candidates for the engine behind an FRB. They occur on the required millisecond timescale. They involve a compact object, and they are capable of releasing titanic amounts of energy. For years, this remained a compelling but circumstantial theory. The evidence was strong, but it was based on extrapolation from weaker flares seen from magnetars within our own galaxy. What was needed was a smoking gun. That gun finally fired in April of 2020. Astronomers were monitoring a known magnetar within our own Milky Way, named SGR 1935 plus 2154, which had been unusually active. Then on April 28th, something extraordinary happened. This nearby magnetar, a mere 30,000 light-years away, unleashed a double-barreled blast. It let out a giant flare in X-rays that was detected by satellites orbiting Earth. But at the exact same moment, radio telescopes in Canada and the United States picked up an incredibly bright, millisecond duration radio burst coming from the very same spot in the sky. This radio burst, now known as FRB 2024-28A, was a watershed moment. While this galactic event was thousands of times less energetic than the most powerful extragalactic FRBs, its properties were a perfect match in every other way: the short duration, the spectral shape, the immense brightness. For the first time, there was an unambiguous link. A known magnetar had produced a fast radio burst. This was the proof that the magnetar model was on the right track. It demonstrated conclusively that the physical processes occurring on these ultramagnetic neutron stars are indeed capable of generating the type of signals we see from across the universe. The galactic event was like finding a scaled-down laboratory version of the cosmic phenomenon, confirming that the underlying physics is real and potent. It provided the first direct observational bridge between a theoretical culprit and the crime scene. So the case for magnetars seems strong, especially with that smoking gun detection from within our own galaxy. It's a satisfying piece of the puzzle, but in science, a single clue rarely solves the entire mystery. The critical question now becomes, are magnetars the only source of these bursts? The evidence suggests the answer is a definitive no. While magnetars are a fantastic explanation for many FRBs, particularly the repeaters, the incredible diversity we're seeing in the bursts themselves and their host galaxies points to a universe that is far more creative, employing multiple different engines to produce these brilliant flashes. Think of it like this: if you hear a loud bang, it could be a firecracker, a car backfiring, or a gunshot. The sound alone doesn't tell you the source, you need context. With FRBs, the context is everything. The one-off, non-repeating bursts present the biggest challenge to the idea of a single universal cause. If a magnetar flare explains a repeater, what explains a burst that happens once and is never seen again from that location? That behavior is the hallmark of a cataclysmic, self-destructing event. The leading candidate for these one-time bursts is the merger of two incredibly dense objects. Imagine two neutron stars, each the size of a city but containing more mass than our sun, locked in a gravitational death spiral. For millions of years, they orbit each other, slowly losing energy by emitting gravitational waves. In the final moments, they spiral inward at a significant fraction of the speed of light and collide in a spectacular explosion. This merger is thought to create a black hole and unleash a tremendous blast of energy across the electromagnetic spectrum, an event we know can produce gamma-ray bursts. It is entirely plausible that such a violent final act could also generate a powerful, one-off fast radio burst. This model elegantly explains why we never see a second burst from that location. The source is completely annihilated. Another intriguing possibility for single events is a concept known as a blitzer. This theory proposes the collapse of an overly massive neutron star. Normally, when a star goes supernova, the leftover core is a neutron star, held up against its own gravity by a quantum mechanical force called neutron degeneracy pressure. But what if the resulting neutron star is just a little too heavy? It might be temporarily supported by its incredibly rapid rotation, like a cosmic top spinning so fast it doesn't immediately collapse. But as it loses spin energy over time, perhaps thousands of years, it eventually slows down just enough for gravity to win. In an instant, the neutron star would collapse into a black hole. Theorists suggest that during this sudden collapse, the magnetic field of the neutron star, which is no longer anchored to a physical object, is snapped off and ejected into space. This process of magnetic field detachment could release an immense, one-time flash of radio waves, a fast radio burst. The blitzer is an attractive idea because it provides a clear reason for a single, enormously energetic event that leaves no persistent source behind. And then we venture into the truly exotic territory, where physicists let their imaginations run wild within the constraints of mathematics. One such idea involves cosmic strings. These are not strings in the everyday sense, but hypothetical, one-dimensional defects in the very fabric of space-time, relics from the universe's earliest moments. Theorized to be thinner than a proton but stretching across the entire cosmos, they would possess immense mass. If two such strings intersected, or if a string loop collapsed, it could theoretically release a phenomenal amount of energy in a gravitational wave shock. This shock might then interact with surrounding plasma to generate a brilliant radio burst. While entirely speculative, cosmic strings represent the kind of thinking required when conventional explanations fall short. And of course, we cannot ignore the elephant in the room, the possibility of artificial origins. Could some FRBs be evidence of extraterrestrial technology? The idea of powerful interstellar beacons used for propulsion or communication has been seriously proposed by astronomers, though it remains the least likely explanation for most scientists. The reason it's difficult to completely dismiss is a peculiar property of some bursts called high brightness temperatures. To achieve such intense emission, the particles producing the radio waves would need to be moving in near-perfect synchrony, a phenomenon known as coherent emission. While nature has ways of doing this, like the natural lasers in interstellar gas clouds or the emission from pulsars, the degree of coherence in FRBs is extreme. This has led some to note that such efficient, focused emission is reminiscent of human technology, like radar. However, the astronomical energy requirements make it an unlikely scenario for all but the most advanced civilizations, and the total lack of any patterned information in the signals makes a technological origin a hypothesis of last resort. It's a fascinating thought, but the principle of Occam's razor, that the simplest natural explanation is usually the correct one, strongly favors astrophysical sources. Ultimately, the sheer variety of FRB behaviors and their host galaxies is the most compelling argument against a single, unified theory. We have repeaters and one-offs. We have bursts coming from tiny, star-forming dwarf galaxies and from massive, quiet spirals. We even have that one repeater from an ancient globular cluster, an environment where young magnetars shouldn't exist. This diversity strongly suggests that fast radio burst is not the name of a single phenomenon. but rather a descriptive term for a final, common signal that can be produced by several different cosmic cataclysms. It might be that magnetars are responsible for the repeating signals, while neutron star mergers or blitzars account for the one-offs. The universe appears to have more than one way to create a millisecond flash that can outshine galaxies, and our task now is to match each type of burst to its specific cosmic engine. Just when we thought the repeating FRBs had given us the ultimate clue, the universe unveiled yet another layer of complexity, one that points to an intricate cosmic clockwork. The discovery that some of these repeaters are not just sporadic but follow a strict, predictable schedule was a revelation that sent theorists back to their chalkboards. The star of this show is a source known as FRB 1809-16.J0158+65, detected by the CHIME telescope in Canada. After observing it for more than 400 days, astronomers noticed an incredible pattern. This source would become active, firing off multiple bursts over a period of approximately 4 days. Then, as if a switch had been flipped, it would fall completely silent for the next 12 days. This cycle of activity and dormancy repeated with astonishing regularity every 16.35 days. It was the first clear evidence of periodicity in an FRB, and it transformed our view of the source from a simple erratic engine to a finely tuned celestial mechanism. This predictable timetable is a treasure trove of information. In astronomy, periodicity is a powerful diagnostic tool. When something in the cosmos repeats on a strict schedule, it almost always points to an orbital motion. The 16-day cycle strongly suggests that the object producing the FRB is not alone. It is locked in a gravitational dance with a companion. This realization immediately narrows down the possible scenarios, pointing us toward a binary system. The central question then becomes, what is the nature of this cosmic duo, and how does their orbital dance govern the bursts? The leading hypothesis involves a neutron star, likely a magnetar, in orbit around a massive, luminous companion star, perhaps a B-type star. B stars are known for their rapid rotation and for casting off a disk of gas around their equator, like a spinning sprinkler creating a watery halo. In this model, the 16.35-day period is simply the orbital period of the neutron star around its companion. But the key to the active window lies in a phenomenon called precession. Just as a spinning top wobbles slowly as it rotates, the spin axis of a neutron star can also wobble or precess over time. If the radio emission is beamed from the neutron star's magnetic poles, like a lighthouse, this precession would cause the beam to sweep across space in a predictable pattern. For about 4 days in its cycle, that lighthouse beam would be pointed in our direction, and we would see the flashes. For the remaining 12 days, the beam is pointed away from Earth, and from our perspective, the source is silent. This is a beautifully elegant explanation that accounts for both the periodicity and the specific duration of the active window. However, the companion star itself might also play a more direct role in creating the on-off cycle. If the companion is a massive star losing material in a stellar wind, the neutron star could be plowing through a denser, more turbulent part of that wind at a specific point in its orbit. Imagine a comet that vents gas and dust most actively when it is closest to the Sun. Similarly, the FRB engine might be turned on when the neutron star encounters a dense cloud of plasma near its companion, with the interaction triggering the burst. The active window would then correspond to the part of the orbit where the environment is just right for producing the brilliant radio flashes. The quiescent period would be when the neutron star is traveling through a much thinner region of space, where the conditions aren't met for the same level of activity. Beyond stellar companions, could the periodicity point to something even more exotic? Some theorists have explored the possibility of a planetary mass object orbiting the neutron star. In this scenario, the planet's gravity could periodically disturb the magnetosphere of the neutron star. perhaps triggering avalanches on its crust or altering its magnetic field in a way that leads to bursts. While less favored than the binary star model, it underscores the creative thinking spurred by this discovery. The precise clockwork of FRB 1809-16 offers a unique probe into the geometry and environment of the source, something we could never achieve with one-off bursts. It allows us to move from asking, "What is it?" to asking, "How is it configured?" This is a monumental leap, transforming the FRB from a mere flash into a dynamic system whose inner workings we can begin to map. This predictable clockwork, where bursts fire on a strict schedule, gives us an incredible window into the geometry of these systems. But to truly understand the engine itself, we need to listen even more closely to the individual bursts. And when we do, we notice something truly bizarre, a subtle fingerprint in the signal that acts like a secret message about the environment right next to the source. This is the mystery of the downward drifting tones, a phenomenon often called chirping. Imagine you're listening to a bird call, a quick chirp that starts on a high note and swiftly slides down to a lower one. Now imagine that same sound, but produced by a cosmic object with the power of 100 million suns. That is essentially what astronomers see in the data for many repeating fast radio bursts. When they zoom in on a single millisecond burst, they often find that it isn't just a single pop of radio noise. Instead, it's composed of multiple, even finer subpulses. And each of these subpulses has a distinct musical quality. It begins at a higher frequency and then rapidly glides downward in pitch. In a visual representation called a dynamic spectrum, where time runs horizontally and frequency runs vertically, this creates a striking pattern of diagonal stripes, each one sloping downward to the right like a set of cosmic stair-steps descending into lower energies. This chirp is far more than a curious audio effect. It is a direct consequence of the laws of physics and a crucial clue. You'll recall the dispersion measure, the effect where the entire burst is delayed by its journey through intergalactic plasma, with lower frequencies arriving later than higher ones. The chirp is like a miniature, supercharged version of that same principle happening right next to the source. The leading explanation is that before the radio waves even begin their billion-year journey across the universe, they must first pass through a dense, turbulent, and intensely magnetized screen of plasma that surrounds the central engine. This could be a cloud of ejected material from a previous flare, a nebula powered by the neutron star's wind, or the magnetosphere of the object itself. As the radio waves travel through this local plasma screen, they interact with the free electrons within it. Just like with the intergalactic dispersion, lower frequency waves are slowed down more effectively than their higher frequency counterparts. But because this plasma is so much denser and more complex than the diffuse gas between galaxies, the effect is dramatically amplified and happens on a much smaller scale. Think of it like sound traveling through different materials. Sound moves faster through air than through water. Now imagine a complex sound wave hitting a thin but dense wall of water. The high-pitched components might punch through almost immediately, while the lower-pitched components get bogged down for a fraction of a second longer. In the case of an FRB, the subpulses we see are likely generated in a rapid series by the central engine. As each pulse propagates outward, it immediately hits this local plasma screen. The higher frequencies in the pulse emerge first, while the lower frequencies are temporarily trapped, creating that characteristic downward drift in the data. This makes the chirp an incredibly powerful diagnostic tool. For astronomers, it's like being handed a key to the immediate neighborhood of the FRB source. By meticulously measuring the rate of the frequency drift, how quickly the tone slides from high to low, scientists can calculate the density and the magnetic field strength of this surrounding plasma. A very rapid, steep chirp suggests the waves are moving through an incredibly dense and magnetically chaotic environment. A slower, more gradual drift might point to a more diffuse, orderly region. It's a way to probe conditions that are otherwise completely invisible to us, offering a glimpse into the dynamic and violent space just light seconds or light minutes away from one of the most powerful engines in the universe. This subtle musical signature, therefore, transforms each burst from a simple flash into a complex sonar ping, echoing through the heart of the storm and revealing secrets about the cradle of cosmic violence itself. But the clues hidden within these bursts extend far beyond their timing and tones. They are also encoded in the very orientation of the radio waves themselves. This brings us to a subtle yet profoundly revealing phenomenon known as Faraday rotation, and the observations of it in some FRBs are nothing short of extraordinary. To understand Faraday rotation, think of a radio wave not just as a wave of energy, but as a wave that vibrates in a specific direction, like a rope being shaken up and down or side to side. This property is called polarization. Now, imagine this polarized wave traveling through a cloud of ionized gas or plasma that is threaded with a magnetic field. As the wave interacts with the free electrons and the magnetic field, something remarkable happens. The plane of its vibration slowly twists like a screw rotating as it moves forward. The stronger the magnetic field and the denser the plasma, the more the wave's polarization plane will rotate. For most cosmic radio signals, like those from pulsars within our galaxy, the amount of Faraday rotation is relatively small. It's a measurable effect, but it indicates magnetic fields of a strength we would expect from the general interstellar medium. However, when astronomers measured the Faraday rotation for the repeating burst FRB 121102, they were astounded. The rotation was not just large, it was off the charts, 1,000,000 times more extreme than anything seen from a source within the Milky Way. To achieve such a dramatic twisting, the radio waves must have passed through an environment of almost unimaginable magnetic fury. The calculations point to a field strength billions of times more powerful than the magnetic field that permeates the space between stars in our own galaxy. This is not the gentle magnetic field of interstellar space. This is a magnetic field of apocalyptic intensity. Where in the universe could such a field exist? The answer points overwhelmingly to a very specific and extreme environment, the immediate vicinity of a young magnetar. More precisely, it points to what is known as a magnetar wind nebula. Picture a newborn magnetar, a city-sized object with a magnetic field so powerful it can distort the shape of atoms. This star is not quiet, it is erupting with giant flares and spinning rapidly, blowing out a relentless wind of charged particles that race away at near light speed. This wind, however, cannot escape easily. It slams into the slower-moving debris left over from the supernova that created the magnetar, creating a massive, expanding bubble of hot, magnetized plasma that envelops the central star. This is the magnetar wind nebula, a cauldron of magnetic fields and energetic particles. It is within this dense, magnetized cocoon that the extreme Faraday rotation is thought to occur. Before an FRB's radio waves can even begin their journey across the universe, they must first traverse this nebula. As they do, they are forced to pass through a region where the magnetic field is not just strong, but also incredibly ordered and coherent. The twisting of the polarization plane becomes a direct measuring stick for the magnetic power contained within this nebula. The fact that FRB 121102 shows such extreme Faraday rotation is therefore some of the strongest circumstantial evidence we have that this repeater is indeed powered by a magnetar, and one that is very young, still nestled within the turbulent shell of its own birth. It's as if the burst carries a permanent imprint of the monstrous magnetic field from its place of origin, a fingerprint that survives its journey of billions of light years to tell us exactly what kind of monster lurks at the source. For all their raw power and brilliance in the radio part of the spectrum, fast radio bursts hold onto their secrets with a curious kind of stubbornness, presenting what is perhaps one of the most frustrating observational challenges. their eerie silence elsewhere. When astronomers detect one of these colossal bursts, it sets off a frantic worldwide scramble. Within seconds, alerts are automatically sent to observatories across the globe and in space, commanding powerful telescopes to drop whatever they are doing and point their lenses, mirrors, and detectors toward the source. They are hunting for a counterpart, any flash, glow, or flicker of light at any other wavelength that might accompany the radio blast. The expectation is that an event capable of shaking the cosmos with such force should not be a one-trick pony. It should light up the sky across the entire electromagnetic spectrum. Yet, for the overwhelming majority of FRBs, the result is the same, a profound and puzzling silence. The radio burst arrives like a thunderclap, but there is no lightning. No X-ray flash, no gamma-ray pulse, not even a faint optical glimmer. The universe, it seems, is firing a cannon that only makes a sound we can hear on one very specific frequency. This absence is a major headache for theorists because it directly contradicts what we would expect from some of our best guess models. Consider the leading candidate for the one-off bursts, the merger of two neutron stars. We know this is a cataclysmic event because we have actually observed it before. In 2017, the collision of two neutron stars was detected through both gravitational waves and a brilliant flash of light known as a kilonova. This event produced a fireworks show of radiation, emitting a tremendous burst of gamma rays followed by a bright afterglow that shone for days in optical and infrared light, created by the radioactive decay of heavy elements like gold and platinum forged in the cosmic furnace. If a neutron star merger were responsible for an FRB, we would expect a similar, unmistakable signature, a multi-wavelength counterpart that would be a smoking gun. The fact that we almost never see this for one-off FRBs forces us to ask a difficult question. Are we wrong about the merger model, or is the radio burst somehow produced in a way that is completely decoupled from the expected light show? The mystery only deepens when we look at the repeater FRBs and their connection to magnetars. We have direct proof from our own galaxy that magnetars can produce radio bursts alongside X-ray flares, as we saw with the event from SGR 1935 plus 2154. That was a simultaneous two-part event, so why don't we see the same thing for the extragalactic repeaters? There are a few compelling possibilities. The first is a matter of distance and beaming. The galactic magnetar flare was incredibly bright in X-rays, but it was also very close. When we look at a repeater billions of light years away, the same X-ray flare would be diluted to an incredibly faint whisper by the time it reaches us, possibly falling below the detection threshold of even our most sensitive space-based telescopes. Furthermore, the radio emission and the X-ray emission might not be beamed in the same direction. The radio burst could be like a narrow lighthouse beam pointed directly at us, while the higher energy X-rays might be emitted in a wider, less focused cone that misses the Earth entirely. We might only be seeing a sliver of the total event. Another intriguing idea is that the environment around the source itself is acting as a filter. Imagine the FRB engine is nestled deep inside a dense cloud of material, like the Magnetar Wind Nebula we discussed earlier. The brilliant flash of radio waves might be able to escape this fog, but higher energy radiation like X-rays and gamma rays could be absorbed and reprocessed by the surrounding debris, their energy converted into lower energy heat that simply isn't noticeable from such a vast distance. The FRB would be the only part of the explosion that manages to punch its way through the cosmic murk and reach our detectors. In this scenario, the lack of a counterpart isn't a sign of a weak event, but rather evidence of a very specific and dense local environment that fundamentally alters the signal we receive. This relentless search for counterparts is a high-stakes game of cosmic timing and coordination. The problem is that the follow-up observations, even when triggered automatically, take time. By the time an optical telescope has slewed to the correct coordinates, precious seconds or even minutes have passed. If the counterpart is a brief millisecond flash of optical light, a true cosmic flashbulb, it would be long gone before any telescope could catch it. We are trying to capture an event that is over in an instant with instruments that, by necessity, move on a timescale of minutes. This has led to the development of dedicated, wide-field optical telescopes that can scan large swaths of the sky continuously, hoping to catch a serendipitous flash at the exact moment an FRB goes off. It is a technological race against the clock, one where a single, successful detection could unlock the entire mystery. Ultimately, the missing counterparts force us to confront the possibility that FRBs are, in essence, radio-only phenomena. Their immense power might be focused almost exclusively into the radio band through a highly efficient process called coherent emission, which is far more effective at producing radio waves than it is at producing light at other wavelengths. This would mean the engine is specifically tuned by its very nature to create a brilliant radio flash without wasting much energy on the rest of the spectrum. While this explains the observational silence, it places even stricter demands on our theoretical models, requiring us to envision a cosmic engine that is not only unbelievably powerful but also extraordinarily specialized. The great multi-wavelength silence surrounding fast radio bursts is not an absence of evidence. It is evidence in itself, pointing toward a reality that is more complex and exotic than our standard cosmic explosion models can easily accommodate. While the search for counterparts from distant galaxies often yielded silence, our own cosmic backyard held a surprise that would change the entire conversation. The tension between theory and observation was resolved not by a signal from billions of light years away, but from an object practically on our galactic doorstep. This brings us to the watershed moment of April 2020, when a known magnetar within the Milky Way, named SGR 1935 + 2154, decided to speak up in a way no one had ever heard before. This object, located about 30,000 light-years away in the constellation Vulpecula, had been known for years as a soft gamma repeater, a type of magnetar prone to occasional outbursts of high-energy radiation. But on April 28th, it did something extraordinary. It unleashed a double-barreled blast that was detected simultaneously by two very different types of instruments: satellites monitoring X-rays and gamma rays and ground-based radio telescopes. The X-ray component of the event was impressive in its own right, a giant flare that saturated detectors on several spacecraft, including NASA Wind and ESA's integral missions. But the real shock came from the radio band. As the X-ray flare erupted, two radio telescope projects captured something unprecedented. In Canada, the CHIME telescope, which is specifically designed to scan huge areas of the sky for fast radio bursts, detected an incredibly bright, millisecond-long radio pulse coming from the exact direction of the magnetar. At almost the same instant, a much simpler experiment in the United States called STARE-2, which consists of just 3 homemade radio antennas placed hundreds of miles apart, also picked up the signal. The STARE-2 detection was crucial because it was so sensitive to bright, nearby events. The data showed a radio burst so powerful that if it had occurred in a nearby galaxy, it would have been unmistakably classified as a fast radio burst. For the first time in history, a magnetar in our own galaxy had produced an FRB. The significance of this detection cannot be overstated. It was the smoking gun that astrophysicists had been searching for. For years, the magnetar model had been a compelling but circumstantial theory, based on extrapolating from the known properties of these objects. Now there was direct observational proof. A magnetar had produced a radio burst with all the hallmark characteristics: millisecond duration, intense brightness, and the telltale frequency structure. This single event, now officially catalogued as FRB 2024-28A, provided the first concrete link between a specific class of celestial object and the mysterious FRB phenomenon. It validated decades of theoretical work and instantly made magnetars the leading candidate for explaining at least a significant fraction of the fast radio bursts we detect from across the universe. However, this breakthrough also ignited a nuanced and ongoing debate within the scientific community, centered on a critical question. Was this galactic event a true FRB, or was it something subtly different? The point of contention lies in the energy scale. The radio burst from SGR 1935 plus 2154 was indeed spectacular, but when its energy was calculated, it fell short of the most powerful extragalactic FRBs by a factor of about 1,000. It was in essence a scaled-down version. To some researchers, this distinction is crucial. They argue that while the magnetar burst confirms the underlying physical mechanism, that highly magnetic neutron stars can produce brilliant radio flashes, the events we see from other galaxies are in a league of their own, perhaps involving even more extreme versions of magnetars or entirely different processes altogether. In this view, our galactic neighbor provided a helpful analog, but not a perfect match. On the other side of the debate are those who see the energy difference as a matter of distance and perspective, not a fundamental difference in kind. They point out that the range of energies seen in extragalactic FRBs is itself enormous, spanning several orders of magnitude. The burst from SGR 1935 plus 2154 fits comfortably within the lower end of this observed distribution. Furthermore, if a magnetar can produce a burst of this power, it is not a huge leap to imagine that a younger, more energetic, or more violently erupting magnetar in a distant galaxy could produce a burst 1,000 times more powerful. The underlying physics of magnetic reconnection or a starquake can, in theory, be scaled up to those immense energies. For these scientists, the galactic event was not just an analog. It was a direct observation of the same phenomenon, simply observed from a much closer vantage point, allowing us to see a fainter example that would otherwise be lost in the noise if it came from a distant galaxy. This debate is more than just academic semantics. It gets to the heart of whether FRBs are a unified class of events. The detection from our galactic magnetar powerfully supports the idea that magnetars can produce the repeating variety of FRBs. But it does not necessarily prove that all FRBs, particularly the incredibly energetic one-off events, are caused by magnetars. It is entirely possible that the universe employs multiple engines. The event from SGR 1935 plus 2154 gave us the key to one door, confirming a major pathway to creating these signals. Yet it also reminded us that there may be other, even more powerful doors still waiting to be unlocked. This single outburst from a known object in our own galaxy transformed the mystery from a question of if certain objects could produce FRBs to a focused investigation into how they do it and under what conditions their power can be magnified to the astonishing levels we witness from the deep cosmos. For all the mysteries surrounding their origins, fast radio bursts are rapidly becoming more than just cosmic puzzles to be solved. They are transforming into some of the most powerful tools in the astronomer's toolkit. In a beautiful twist of fate, the very property that first confirmed their extragalactic nature, the dispersion measure, is now being harnessed to conduct a grand cosmic census, an ambitious effort to literally weigh the unseen contents of the universe. This shift in perspective is crucial. From asking what FRBs are, we are now beginning to use them to answer one of cosmology's biggest questions: where is all the normal matter? You'll recall that the dispersion measure, or DM, is the fingerprint left on a burst by its long journey. As the radio waves travel through the tenuous soup of free electrons that fills the space between galaxies, their lower frequencies are slowed down just a tiny bit more than the higher frequencies, causing the signal to smear out in time. The greater the total smearing, the greater the number of electrons the signal has encountered along its path. Think of it like driving through fog. The thicker and more extensive the fog bank, the more your headlights will be diffused. The DM is essentially a readout of the total fog of electrons between us and the FRB. When we know the exact distance to a burst's host galaxy, something we can only get from precise localization, we can turn this DM value into a direct measurement of the average density of matter along that specific line of sight. This is where the mission becomes truly profound. According to our best models of the Big Bang, we have a very good idea of how much ordinary matter, or baryons, the protons and neutrons that make up stars, planets, and us should exist in the universe today. However, when astronomers add up all the visible matter in galaxies, gas, and dust, they find only about half of what the models predict. The rest, often called the missing baryon problem, has been one of cosmology's most persistent headaches. Where did this enormous amount of material go? The leading theory is that it isn't missing at all, but simply hiding in the form of a diffuse, incredibly hot web of gas known as the warm-hot intergalactic medium, or WIM. This WIM is thought to be the filamentary scaffolding of the cosmos, a billion-degree plasma weaving between galaxy clusters, but it is so tenuous and hot that it emits very little light, making it nearly impossible to detect with traditional telescopes. This is the perfect job for fast radio bursts. Each localized FRB acts like a single, brilliant flashbulb sent through the cosmic fog. By analyzing its dispersion measure, we can take a core sample of the universe along that particular path. Now imagine we don't just have one or two such core samples, but hundreds or even thousands, coming from FRBs localized at all different distances and in all different directions. By combining these millions of individual lines of sight, astronomers can begin to construct a three-dimensional map of the distribution of electrons, and therefore ordinary matter, throughout the entire observable universe. It's a technique akin to medical tomography, where multiple X-ray scans are combined to create a 3D image of the inside of a body. In this case, the patient is the cosmos itself. The early results from this ambitious program are already yielding tantalizing hints. Studies comparing the DMs of a growing number of FRBs with the predicted distribution of matter from cosmological simulations show a remarkable agreement. The data suggests that the amount of material detected in the spaces between galaxies is indeed significant, and it appears to be just about enough to account for the universe's missing baryons. Each new FRB detection adds another data point, another pin in the cosmic map, helping to solidify this picture and trace the invisible architecture of the cosmic web. In this grand endeavor, fast radio bursts are no longer the mystery. They have become the key that is helping us solve one of the greatest mysteries of all, the complete inventory of the universe we call home. This shift from mystery to tool represents one of the most exciting developments in modern astronomy. For decades, cosmologists have been grappling with a deeply unsettling accounting error on a universal scale. When we look at the aftermath of the Big Bang, specifically the cosmic microwave background radiation, we get a very precise figure for how much normal matter the protons, neutrons, and electrons that make up everything we can see should exist in the universe today. This is the baryonic matter, yet when astronomers add up all the visible components, all the stars in all the galaxies, all the cool gas clouds, all the dust, the numbers come up short. Significantly short. We can only account for roughly half of the normal matter that our models tell us should be there. This is the infamous missing baryon problem, and it's been a glaring hole in our understanding of the cosmos. It's as if you carefully calculated your household budget, but when you counted the cash in your wallet, you found only half of what you expected. The question is simple and profound. Where is the rest of the universe's ordinary matter hiding? The leading suspect for this cosmic hide and seek is not some exotic form of dark matter, but rather ordinary matter in a form that is incredibly difficult to see. Theorists predicted that the missing baryons aren't gathered into neat galaxies or cool clouds. Instead, they are spread out in a vast, diffuse, and incredibly hot web of gas known as the warm-hot intergalactic medium, or WIM. Picture the cosmic web not as a structure made of galaxies, but as a structure made of filaments of million-degree gas, with the galaxies themselves merely being the dense knots where these filaments intersect. This WIM is a plasma so tenuous and so hot that it emits very little light, making it practically invisible to traditional telescopes that look for the glow of stars or cool gas. It's the universe's hidden infrastructure, and for a long time it remained just a theoretical prediction, frustratingly out of reach. This is where fast radio bursts make their grand entrance as a revolutionary tool. Their unique properties make them almost purpose-built for solving this cosmic mystery. The key, as we've discussed, is the dispersion measure. Every FRB carries an imprint of its journey, a record of every free electron its radio waves have encountered. When an FRB is precisely localized to its host galaxy, we gain two absolutely critical pieces of information: the total dispersion measure, which is the integrated electron count along the line of sight, and the precise distance to the source. With these two numbers, astronomers can perform a simple but powerful calculation. They can subtract the known contributions to the dispersion measure from our own Milky Way galaxy and from the FRB's host galaxy itself. What remains is the dispersion measure attributable solely to the intergalactic medium, the vast, empty space between galaxies. Each localized FRB effectively turns on a flashlight along a specific, narrow path through the cosmic dark. By measuring how much the light from that flashlight has been smeared, we can calculate the density of the fog it passed through. It's like sending a sonar ping through the ocean and measuring the echo to map the seabed, but on a scale of billions of light years. Now imagine doing this not just once, but hundreds or thousands of times, with FRBs detected from galaxies at all different distances and in all different directions. Each burst gives us a single core sample of the universe. By combining these countless individual samples, we can begin to build up a three-dimensional map of the distribution of matter in the spaces we once thought were empty. This technique, often called dispersion measure tomography, allows us to literally weigh the invisible WIM. The early results from this ambitious program are nothing short of spectacular. As the number of well-localized FRBs has grown, a clear picture has begun to emerge. The dispersion measures from these bursts, when plotted against their cosmological distances, align almost perfectly with the predictions of the models that include the warm-hot intergalactic medium. The data strongly suggests that the amount of material detected in these intergalactic voids is indeed significant, and it appears to be just about enough to close the budget gap and account for the universe's missing baryons. It seems the missing matter wasn't missing at all. It was simply hiding in plain sight, or rather in the dark, in the form of a hot, diffuse plasma that fills the cosmic web. With every new FRB detection, we add another pin to this map, solidifying our understanding of the large-scale structure of the universe. In this profound role, fast radio bursts have transcended their identity as mysterious cosmic explosions. They have become precision instruments, allowing us to conduct a grand inventory of the cosmos and finally solve a mystery that has puzzled astronomers for a generation. Of course, it's the question that captures the public imagination like no other, the cosmic elephant in the room that we've only hinted at so far. Could these incredibly powerful, precisely timed flashes be evidence of intelligence beyond our own? The idea that fast radio bursts are not natural phenomena, but rather the product of an advanced extraterrestrial civilization, is a hypothesis that has been seriously entertained by respected figures in astronomy, most notably Harvard's Avi Loeb. The reasoning isn't as far-fetched as it might initially sound. The key lies in the concept of coherent emission. To achieve the staggering brightness temperatures we observe, the radio waves from an FRB must be emitted in perfect lockstep with trillions of photons marching in unison. This is not how most natural astrophysical processes work. They tend to be messy and chaotic, but coherent emission is exactly how our own technology functions. A simple laser pointer or a radar tower produces coherent light or radio waves. The extreme coherence of FRBs, therefore, could be interpreted as a signature of an engineered signal, a deliberate beacon. One particularly imaginative proposal suggests these bursts could be the leakage from unimaginably powerful interstellar transmitters used to propel spacecraft. The concept of a light sail, where a large, thin mirror is pushed through space by the radiation pressure of a laser, is a real technology we are developing on Earth. Now scale that idea up to a cosmic level. An advanced civilization might use a planet-sized antenna to focus a powerful radio beam onto a massive light sail to accelerate it to relativistic speeds. From our distant, off-axis perspective, we wouldn't see the continuous beam, but only a fleeting flash as the sail and its powerful focusing transmitter swept across our line of sight. The millisecond duration and incredible power would be a natural consequence of this engineering, a kind of cosmic lighthouse for interstellar travel. This idea compellingly explains the brevity, the power, and the one-off nature of many bursts. Each flash represents a separate spacecraft being launched on its journey across the galaxy. However, while this is a captivating narrative, the scientific case against an artificial origin has grown overwhelmingly strong with each new discovery. The first and most decisive blow to the idea came with the identification of repeating FRBs. It is exceedingly difficult to imagine a scenario where an advanced civilization would deliberately build a transmitter that fires its incredibly powerful signal in a random, unpredictable, and repeating pattern across the sky, sometimes dozens of times in a single hour, then falls silent for months. This behavior is far more consistent with the natural, chaotic physics of a spinning, precessing, or erupting celestial object than with any purposeful communication or propulsion system. The discovery of periodicity, the strict clockwork schedules of some repeaters, further solidifies this natural explanation. These cycles point directly to orbital mechanics, the predictable dance of binary stars or the wobble of a neutron star, not the operational schedule of an intelligence. Furthermore, the energy requirements for an artificial transmitter are, even by cosmic standards, almost absurdly prohibitive. To create an FRB that appears as bright as the ones we see from billions of light years away, a transmitter would need to focus its energy into an incredibly narrow beam and pour mind-boggling amounts of power into it. The total energy required would be on the scale of the entire energy output of a planet like Earth for centuries or even millennia. While we cannot rule out what a Type Roman II or Roman III civilization on the Kardashev scale might be capable of, it stretches credulity to suggest that such an immense engineering project would be dedicated to what appears, from our perspective, to be a random and wasteful broadcasting mechanism. Natural astrophysical events, which can tap into the gravitational and magnetic energies of entire stars, provide a far more parsimonious and plausible explanation for such raw power. Ultimately, the principle of Occam's razor, that the simplest explanation consistent with the evidence is usually the correct one, leans decisively toward a natural origin. We have now directly linked at least one FRB to a known type of object, a magnetar, within our own galaxy. We have categorized them into repeaters and one-offs, explained their periodicities with orbital dynamics, and used their signals to map the invisible matter of the universe. The alien hypothesis, while a thrilling thought experiment that pushes us to consider all possibilities, has been largely sidelined by the march of empirical data. It serves as a fascinating reminder of how the universe constantly challenges our preconceptions, but in this case, the evidence points not to intelligence, but to the awe-inspiring, naturally violent processes that shape the cosmos. The real story of FRBs is not about who might be sending them, but about the incredible natural forces we are only just beginning to comprehend. But beyond the question of what creates these bursts lies an even more fundamental puzzle, one that speaks to the sheer scale of cosmic violence happening all around us, just outside our field of view. This is the event rate puzzle. Just how many fast radio bursts are actually occurring in the universe? The answer, based on extrapolations from our limited surveys, is absolutely staggering. Current estimates suggest that across the entire observable sky, 1,000 or more of these colossal explosions may be happening every single day. That's more than one per minute, a near-constant fireworks display of millisecond flashes lighting up the cosmos. This number isn't a wild guess, it's a careful statistical calculation. Astronomers take the number of FRBs they actually detect in a given survey, consider the sensitivity of their telescope and the small patch of sky it was monitoring, and then scale that up to account for the whole sky. The result is a universe that is far more dynamic and explosive than we could have imagined just a few decades ago. The reason we don't see this non-stop celestial light show is a simple matter of technological limitation. Our radio telescopes, for all their power, are like looking at the sky through a series of tiny, narrow drinking straws. A telescope like CHIME in Canada has a much wider field of view than most, which is why it has been so revolutionary in detecting thousands of bursts. But even CHIME can only see a fraction of the sky at any given moment. Most other radio dishes are even more restricted, focusing on an area of sky no larger than the full moon. Furthermore, these instruments are not always listening. They are shared facilities used by many astronomers for different projects, from studying pulsars to mapping neutral hydrogen. The time dedicated to specifically hunting for FRBs is limited. This combination of a narrow field of view and limited observing time means that the 1,000-a-day figure represents a cosmic chorus we are largely deaf to. We are catching only the loudest, closest, or most fortuitously placed bursts, a tiny fraction of a percent of the total population. It's like standing in a dark field during a meteor shower. You only see the occasional bright streak that happens to cross your narrow line of sight, completely missing the magnificent spectacle unfolding across the entire heavens. This immense event rate has profound implications for what kind of objects can be responsible. If 1,000 FRBs are going off every day across the universe, then the sources cannot be incredibly rare once-in-a-lifetime events. They must be relatively common occurrences. Think about it this way. If the progenitor of an FRB were an event as rare as the merger of two neutron stars, which might happen only once per galaxy every 10,000 or even 100,000 years, then the probability of us seeing one from a distant galaxy would be infinitesimally small. The fact that we detect so many, even with our limited capabilities, tells us that the engines powering these bursts must be numerous. They must be a standard, recurring phase in the life cycle of certain celestial objects, not the final, unique death throes of exotic pairs. This statistical argument strongly favors models involving objects that are common and can produce multiple bursts like magnetars. There are billions of galaxies in the observable universe, and if each one contains even a handful of active magnetars over its lifetime, the numbers can easily add up to the event rate we infer. The universe must be teeming with these powerful engines, each capable of erupting many times, ensuring that at any given moment, somewhere, a flash is illuminating the dark. But even as we map this constant cosmic fireworks display, a more subtle mystery emerges from the signals themselves, one that concerns not their timing or power, but their very color. It's a puzzle known as the spectral bandwidth enigma. When we tune our radio telescopes across the dial, from the low rumbles of a few hundred megahertz to the high-pitched shrieks of several gigahertz, we find that fast radio bursts overwhelmingly appear within a specific window, typically between about 400 megahertz and 8 gigahertz. It's as if the universe has a favorite radio station, and outside that frequency band, the signals become incredibly faint or vanish altogether. This observed bandwidth forces us to ask a critical question. Is this a fundamental property of the cosmic engine itself, or is it a trick of perception, a filter imposed by the long journey through space or the limitations of our own technology? First, let's consider the possibility that the narrow bandwidth is intrinsic to the source. Imagine a musical instrument like a flute, which naturally produces sound within a specific range of notes. It simply cannot produce the deep bass of a tuba or the high pitch of a piccolo. In a similar way, the physical mechanism that generates an FRB might be naturally tuned to emit most efficiently within this particular radio band. For the leading magnetar model, the emission is thought to be generated by a process called coherent curvature radiation or synchrotron maser emission. In simple terms, this involves bunches of electrons moving in a coordinated dance along the incredibly curved and powerful magnetic field lines near the star. The frequency of the radiation they produce is directly tied to the strength of the magnetic field and the energy of the electrons. It's possible that the conditions in these extreme environments are just right for amplifying radio waves most effectively in that few gigahertz range, making the source itself a radio specialist, naturally quiet at frequencies far above or below its peak output. If this is the case, then the observed bandwidth is a direct fingerprint of the physics happening on the surface of or within the magnetosphere of a neutron star. However, the journey of a radio wave across billions of light years is anything but a clean, straight path, and this opens up the second major explanation: propagation effects. The radio signal must travel through a complex and often messy medium, the tenuous plasma that fills the space between stars and galaxies. This plasma can act like a cosmic filter, selectively absorbing or scattering certain frequencies. At the lower end of the spectrum, below a few hundred megahertz, a phenomenon called free absorption becomes significant. As the radio waves pass through clouds of ionized gas, they can interact with free electrons, effectively being absorbed and their energy converted to heat. The lower the frequency, the stronger this absorption effect becomes. It's analogous to how red light penetrates fog better than blue light. For FRBs, the very low-frequency radio waves might be getting lost in the cosmic haze before they ever reach our telescopes. On the other high end, at frequencies above 8 GHz or so, the signal might be weakened by a different process called scatter broadening. Tiny density fluctuations in the interstellar and intergalactic plasma can cause the radio waves to scatter, taking slightly different paths to reach us. This scattering has a smearing effect, like looking at a light through a frosted glass window, and it becomes more pronounced at higher frequencies. This scattering can stretch and dilute a sharp millisecond burst into a longer, fainter signal that blends into the background noise, making it undetectable. So, the sweet spot for detecting FRBs might simply be the frequency band where the signal can travel from its source to our telescopes with the least amount of interference. We must also confront a more pragmatic but equally important factor: our own technological blind spots. Every radio telescope is designed with a specific bandpass, a range of frequencies it is optimized to receive, much like a car radio that can only tune to stations between, say, 88 and 108 MHz. The world's most prolific FRB hunters, like the CHIME telescope in Canada, are exceptionally good at scanning large areas of the sky, but they are specifically tuned to operate in a band from 400 to 800 MHz. Other major telescopes, like ASCAP in Australia, operate around 1.4 GHz. If an FRB were to occur primarily at a frequency of, say, 50 MHz or 30 GHz, our most powerful and wide-field survey instruments would be completely deaf to it. They are simply not listening on those channels. This creates a powerful observational bias. We find FRBs where we look for them. It is entirely possible that a whole population of low-frequency or high-frequency FRBs exists, but they remain hidden from our current technological view, like a secret broadcast on a wavelength our radios cannot receive. The narrow observed bandwidth may be less about the universe's preferences and more about the limitations of our own ears on the cosmos. Untangling this enigma is a major focus of next-generation astronomy. The key will be to observe the same FRB with multiple telescopes operating at vastly different frequencies simultaneously. If a burst detected by CHIME at 600 MHz is also seen by a telescope like the Green Bank telescope at 2 GHz and another instrument at 10 GHz, and all show a similar signal strength, that would strongly suggest the source emits broadly across the spectrum. If, however, the higher frequency telescopes see nothing, that would point toward propagation effects or an intrinsic cutoff. Early attempts at such multi-frequency campaigns have been challenging, often finding that repeaters are silent at higher frequencies when they are active at lower ones, adding another layer of complexity to the mystery. The spectral bandwidth of FRBs is therefore not a minor technical detail. It is a fundamental clue that intertwines the nature of the source engine, the structure of the cosmic web, and the capabilities of our own technology. Decoding it will require us to listen to the universe across the entire radio dial, searching for the missing notes in this cosmic symphony. Alongside the subtle downward drift of frequencies, another distinct fingerprint is sometimes left on a fast radio burst, one that speaks not of the source itself but of the turbulent seas it must navigate on its journey to us. This is the phenomenon of scattering, where an otherwise sharp millisecond burst arrives at our telescopes looking as if it has been stretched and smeared across time. Imagine shouting a single, quick word across a wide, rocky canyon. Instead of hearing a clean echo, you hear your voice reflected back in a blurred, drawn-out rumble as the sound waves bounce off the uneven surfaces at slightly different times. A similar thing happens to an FRB when its radio waves encounter clumpy, turbulent clouds of ionized gas or plasma along its path. These clouds act like cosmic fog banks filled with microscopic irregularities, causing the signal to take multiple, slightly different routes around the density fluctuations. The higher frequency waves, being more resilient, tend to punch through with less delay, while the lower frequency waves get bogged down more effectively, taking the scenic route. The result is that a single, instantaneous flash gets transformed into a signal with a long, fading tail that can last for many milliseconds after the main pulse, especially noticeable at the lower end of the radio band. This scattering tail is far more than just a distortion to be corrected. For astronomers, it is a powerful diagnostic tool. By carefully measuring how much a burst has been smeared, scientists can calculate the level of turbulence and the electron density in the plasma clouds it passed through. The amount of scattering is exquisitely sensitive to the smallest structures in the ionized gas. A little bit of scattering indicates a relatively smooth, calm interstellar highway. A great deal of scattering, however, points to a path littered with exceptionally dense and violently churning plasma, the kind of environment you might find near the heart of a star-forming region or in the chaotic wake of a recent supernova explosion. It's like being able to gauge the roughness of a sea by how much a lighthouse beam is distorted as it passes through the storm. This leads to a fascinating pattern and a crucial clue. When researchers analyze large samples of FRBs, they find a tremendous range in the amount of scattering they exhibit. Some bursts arrive remarkably clean and sharp, suggesting they traveled through relatively empty intergalactic space. Others, however, show extreme scattering, their signals stretched out as if they fought through a cosmic hurricane. Intriguingly, there appears to be a correlation. The bursts with the most severe scattering often seem to be the ones that also have the highest overall dispersion measures. This combination suggests that these signals didn't just travel a long distance, they also passed through an especially dense and turbulent environment, likely very close to their birthplace. The most plausible explanation is that these heavily scattered FRBs originated in regions brimming with activity, such as the dense central cores of their host galaxies, or within vibrant stellar nurseries shrouded in the hot, ionized gas of newly formed stars. The scattering tail, therefore, acts as a cosmic travel log, revealing not just the total distance traveled but the specific, stormy neighborhoods the burst had to escape from before it could even begin its billion-year journey across the universe. Moving down the radio dial to the lowest frequencies presents an entirely new set of challenges and revelations in the hunt for these cosmic flashes. While many telescopes are tuned to the gigahertz range, a determined search has been underway at the opposite end of the spectrum, listening for bursts at frequencies below 400 megahertz, even down to the FM radio band and beyond. This is the domain of immense radio telescopes like LOFAR, the low-frequency array, which spans multiple European countries with thousands of small antennas working in concert. Peering into this low-frequency window is like trying to see through a dense, turbulent fog. The primary obstacle is a dramatic increase in a phenomenon we've touched on: scattering. At these lower frequencies, the effect of passing through interstellar and intergalactic plasma is magnified exponentially. A sharp, millisecond burst can be stretched out over seconds or even minutes, its signal smeared into a long, slow whisper that blends seamlessly into the background radio static of the universe. Detecting such a distorted signal requires incredibly sophisticated signal processing and a great deal of patience. Adding to the difficulty is the cacophony of human-generated radio frequency interference at these wavelengths. The same band that astronomers are trying to listen on is crowded with signals from television broadcasts, FM radio stations, aircraft radar, and countless other terrestrial technologies. Distinguishing a faint, scattered cosmic signal from this relentless roar of human activity is perhaps the ultimate test of observational skill. For a long time, this led to a critical question: do fast radio bursts even emit significant power at these low frequencies, or does their signal simply fade away below a certain cutoff? The answer would reveal a great deal about the underlying emission mechanism. If the bursts were completely absent at low frequencies, it would suggest that the physical process generating them has a natural minimum frequency, much like a musical instrument that cannot produce notes below a certain pitch. This would strongly constrain theoretical models, favoring mechanisms that are inherently inefficient at long wavelengths. The breakthrough came when telescopes like LOFAR, along with the giant meterwave radio telescope in India, began to succeed in this difficult hunt. They confirmed that fast radio bursts do indeed reach down into the low-frequency realm, but they arrive in a profoundly altered state. The detections, particularly of the famous repeater FRB 121102 at frequencies around 150 MHz, showed bursts that were almost unrecognizable compared to their high-frequency counterparts. Instead of a sharp spike, the signal was stretched over hundreds of milliseconds, sometimes even longer, by the intense scattering along its path. This heavy scattering is itself a valuable clue. It implies that the radio waves on their journey pass through an exceptionally turbulent and dense screen of plasma. This supports the idea that this repeater is embedded in a complex environment, like the magnetar wind nebula we discussed earlier, with the low-frequency waves being most susceptible to the fog. What does this tell us about the engine itself? The mere fact that we see emission at such low frequencies is a crucial puzzle piece. It suggests that the same fundamental process that creates the brilliant flash at 1.4 GHz is also capable of generating radio waves hundreds of times longer in wavelength. This argues against models where the emission is generated in an extremely compact region that would naturally filter out low frequencies. Instead, it points toward emission mechanisms that can operate across a very broad band. However, the intensity of the low-frequency emission relative to the high-frequency signal is also telling. In some cases, the burst appears much weaker at low frequencies, which could mean the source's intrinsic emission does indeed drop off, or it could simply be that the propagation effects are so severe that most of the signal is scattered away before we can detect it. Unraveling this requires observing the same burst simultaneously at high and low frequencies, a difficult coordination task that is a major goal for observatories worldwide. Each low-frequency detection, despite its distorted appearance, adds a new constraint, helping scientists refine their models of how these cosmic engines actually work, proving that even the most stretched-out whisper from the cosmos can carry a profound message. While low frequencies present the challenge of a cosmic fog, pushing our observations to the opposite end of the radio dial reveals a different kind of frontier, one defined not by scattering but by an unexpected quiet. If we tune our telescopes to frequencies above 2 GHz, venturing into the centimeter wave band and beyond, the cacophony of fast radio bursts largely fades away. Detections at these high frequencies have been notably scarce, creating a puzzling cutoff in our view of these events. This high-frequency mystery forces us to confront a critical question. Is the universe simply not making many FRBs at these shorter wavelengths, or are we failing to hear them? One compelling possibility is that this scarcity is intrinsic to the burst engines themselves. The physical process responsible for the coherent radio emission may have a natural peak efficiency, much like a musical instrument that has a richest tone in a specific register but produces weaker harmonics at much higher pitches. For the leading theoretical models, such as synchrotron maser emission or coherent curvature radiation near a magnetar, the output spectrum is not flat. It is expected to fall off sharply beyond a certain frequency. The intense magnetic fields and particle energies involved might naturally favor the generation of radio waves in the 1 to 3 GHz range, with the power dropping off dramatically as we move higher. In this scenario, the lack of high-frequency detections isn't a problem with our observations. It is a fundamental fingerprint of the emission mechanism, telling us that the cosmic engine simply isn't revving as high on that part of the dial. However, we must also consider the journey the signal takes. Just as low-frequency waves can be absorbed, high-frequency waves can face their own form of attenuation. A process known as free absorption can occur when radio waves pass through particularly dense and hot plasma. In this interaction, photons are absorbed by free electrons without the electrons becoming bound to an ion. This effect is more pronounced at lower frequencies, but in extremely dense environments, it can still significantly diminish higher frequency signals as well. If an FRB source is deeply embedded within a dense nebula or a star-forming region, the surrounding soup of ionized gas could act like a high-frequency filter, selectively blocking the shorter wavelength radiation from ever escaping its local environment. What we perceive as a high-frequency deficit might actually be a cosmic curtain, drawn closed by the very material that cradles the source. We also cannot ignore a more practical, terrestrial challenge, the simple lack of dedicated high-frequency surveys. The hunt for FRBs has been led by telescopes optimized for large field of view observations, and there is a fundamental trade-off in telescope design. Achieving a wide field of view is much easier at lower frequencies. Instruments like CHIME and ASCAP are brilliant at scanning huge swaths of sky, but they operate in bands below 1.5 GHz. High-frequency radio dishes like the massive Effelsberg telescope in Germany or the very large array in its higher frequency configurations typically have much narrower fields of view. They are like looking at the sky through a pinhole instead of a wide-angle lens. The chance of one of these narrow-field instruments being pointed at the exact right piece of sky at the exact millisecond an FRB goes off is astronomically small. Therefore, the scarcity of high-frequency detections could be a profound observational bias. We are largely deaf to high-frequency FRBs, not because they don't exist, but because our best ears are not designed to listen for them across the entire sky. This makes the few high-frequency detections we do have incredibly precious. When a burst is caught simultaneously at both low and high frequencies, it provides a golden opportunity to measure its full spectral energy distribution. This is the equivalent of seeing the complete rainbow of the burst's radio light rather than just a single color. A flat spectrum where the burst is just as bright at 5 GHz as it is at 1 GHz would point toward one type of emission mechanism. A steeply falling spectrum where the high-frequency emission is much weaker would strongly favor a different set of physical models. Furthermore, without knowing the brightness across the entire radio band, we cannot accurately calculate the burst's total energy output. If a significant portion of its power is being emitted at high frequencies that we're missing, we could be drastically underestimating the true ferocity of these events. Each tentative high-frequency detection, therefore, is a critical data point in our quest to understand the complete physics of the central engine, helping us to move from a fragmented glimpse to a full-color portrait of cosmic violence. Even as we decipher the unique properties of individual bursts, a grander theoretical challenge emerges, one that seeks to weave all these disparate threads into a single, coherent tapestry. This is the population synthesis challenge, an ambitious effort by astrophysicists to create models that can explain the entire observed menagerie of fast radio bursts, the sporadic repeaters, the clockwork periodic sources, and the enigmatic one-offs, with just a single progenitor type or a small family of related cosmic engines. The goal is nothing less than a unified theory of FRBs, a framework that can account for the staggering diversity we see without resorting to a new exotic explanation for every new observation. It's a cosmic accounting problem of the highest order, and the ledger is incredibly complex. Any successful model must be able to reproduce the vast range of observed characteristics. Why do the energies of these bursts vary by a factor of thousands or even millions? Why do some sources flash dozens of times in an hour while others are never heard from again? How can we explain bursts that look like simple spikes on our instruments alongside others that break apart into intricate patterns of downward drifting sub-pulses? And perhaps most perplexingly, how does the same model account for FRBs born in the vigorous stellar nurseries of dwarf galaxies and those emanating from the quiet, elderly neighborhoods of massive spirals or ancient globular clusters? A theory that beautifully explains the repeater in a dwarf galaxy must also be able to accommodate the one-off burst from a sedate spiral, or it remains incomplete. One compelling line of thought attempts to weave this diversity into a single life story for a magnetar. In this narrative, the distinction between a one-off burst and a repeater is not a fundamental difference in kind, but rather a difference in age and activity level. Imagine a magnetar at the moment of its birth from a supernova. It is young, wildly energetic, and cocooned within a dense, expanding shell of debris from its explosive origin. In this hyperactive youthful phase, it might experience its most colossal eruptions, enormous cataclysmic flares that could qualify as extremely high-energy one-off FRBs. The surrounding debris could both trigger these immense outbursts and also absorb any higher energy radiation, leaving only the brilliant radio flash to escape. After this turbulent infancy, as the magnetar ages and the surrounding nebula dissipates, its eruptions might become less energetic but more frequent, settling into the pattern of a repeater. The one-off bursts we see would then be the spectacular birth cries of newborn magnetars, while the repeaters would be the more managed, persistent outbursts of their adolescent or adult counterparts. Conversely, another scenario flips this life cycle on its head. What if the one-off bursts represent not the beginning but the end? This theory posits the concept of a final, fatal explosion from a dying magnetar. Recall the Blitzar model, where an overly massive neutron star, temporarily supported by its rapid spin, eventually slows down and collapses into a black hole. This sudden, irreversible catastrophe could unleash one ultimate titanic radio burst, a true one-off event signaling the death of the object. In this picture, the repeaters are the magnetars that are stable enough to continue their existence, periodically releasing energy without crossing the threshold into total collapse. The population would then be a mix of stable, repeating engines and those that are destined for a final, self-destructing blast. Reconciling these ideas with the actual census of FRBs is where the real difficulty lies. The discovery of a repeater in an ancient globular cluster, an environment where young magnetars should not exist, throws a wrench into the simple youth-based model. It forces theorists to invent alternative formation channels, like the accretion-induced collapse of a white dwarf or the merger of two old stellar corpses, which could create a magnetar late in the universe's life. This implies that the population of FRB progenitors might itself be diverse, consisting of both young magnetars from core collapse supernova and old magnetars formed through slower binary evolution. The challenge, then, is to determine if the observed properties of bursts can tell us which formation path their source took. Does a burst from a dwarf galaxy have a different energy signature than one from a massive spiral? So far, the signals themselves have proven frustratingly similar, regardless of their galactic address. The ultimate dream is a model so precise that it can take the observed distribution of burst energies, repetition rates, and host galaxies, and use it to reverse engineer the fundamental properties of the underlying population, their birth rates, their magnetic field strength, their lifetimes. It would be a theory that not only explains what we see, but also predicts what we should find next with more sensitive telescopes. Currently, no single model elegantly ticks every box. The population of fast radio bursts remains a complex mosaic, and the synthesis challenge is a stark reminder that the universe rarely conforms to our desire for simple, neat classifications. Instead, it presents us with a continuum of violence where the same basic physics can manifest in a breathtaking variety of ways, each flash a unique chapter in the life story of some of the most extreme objects in existence. But perhaps the most telling clues are not in the grand statistics of energy or distance, but in the intricate millisecond by millisecond architecture of the bursts themselves. When we zoom in with our most powerful instruments, applying the equivalent of a cosmic slow-motion camera, we discover that no two bursts are exactly alike. This is the mystery of burst morphology diversity, a fascinating puzzle that suggests the engines behind these events are far from simple. The basic signal of a fast radio burst is a sudden spike of radio noise, but when we dissect that spike with microsecond precision, we find a stunning array of shapes and structures. Some bursts are beautifully simple, a single, smooth, symmetrical peak that rises and falls in a clean Gaussian curve. It's the signature of a single, coherent event, a clean explosion with a beginning, a middle, and an end. Others, however, are wildly complex. They break apart into a cascade of multiple subbursts, like a string of firecrackers going off in rapid succession. Some profiles are jagged and chaotic, with irregular peaks and valleys that look more like a seismograph reading from an earthquake than a clean astronomical signal. This incredible variety is a direct window into the heart of the chaos, a way to witness the physics of the emission process unfolding in real time. The simplest explanation for multiple subbursts is a rotational model, akin to the lighthouse effect seen in pulsars. Imagine a highly magnetic neutron star spinning rapidly. Its radio emission is beamed from its magnetic poles, which are offset from its rotational axis. Each time a pole sweeps across our line of sight, we see a flash. If the star's magnetic field is particularly complex, with multiple active regions or hotspots, we might see not one, but several sub-bursts within a single rotation period. The timing between these sub-pulses would then be a direct measure of the star's spin and the geometry of its magnetic field. This model elegantly explains bursts that show a regular, repeating pattern of substructure, as if we're hearing the rhythmic ticking of a cosmic clock. However, not all morphologies are so orderly. The jagged, chaotic profiles point toward a different kind of violence altogether: plasma instabilities. In the extreme environment around a magnetar, the magnetic field is so powerful that it can trap and accelerate plasma to near light speeds. This plasma can become unstable, much like a river flowing too fast develops rapids and whirlpools. These instabilities can trigger a runaway process where energy is released in a frantic, unpredictable series of eruptions. Think of it like a solar flare on our sun, but scaled up to unimaginable intensities. The jagged burst profile would be the radio signature of magnetic reconnection events happening in a turbulent, seething storm of plasma, each spike representing a separate magnetic field line snapping and reconnecting. The complex morphology is a direct recording of that storm's fury. Another compelling idea involves shock waves. If the initial energy release from the central engine, perhaps a starquake or a magnetic reconnection event, propagates outward, it could plow into surrounding material, creating a shock front. As this shock wave moves through clouds of debris or the neutron star's own wind, it can accelerate particles, causing them to emit radio waves. The complex shape of the burst could then map the interaction of this shock with a clumpy, uneven environment. A dense clump of material would produce a bright subburst. A void would create a dip. In this scenario, the burst morphology becomes a sonar map of the immediate surroundings of the FRB source, revealing the structure of the nebula or the debris field that cradles it. The incredible diversity of shapes we see strongly suggests that there is no single, universal blueprint for a fast radio burst. Instead, the final signal we receive is a complex product of the initial trigger, the structure of the magnetic field, the density of the surrounding plasma, and the journey of the emission through this chaotic realm. Each unique morphology is a frozen snapshot of a unique moment of cosmic violence, offering a detailed, if cryptic, diary of an event happening on an object smaller than a city, from billions of light years away. As we piece together the clues from the radio waves themselves, a far more ambitious hunt is underway, one that seeks to expand our senses beyond the electromagnetic spectrum entirely. This is the frontier of multi-messenger astronomy, a coordinated global effort to catch a fast radio burst in the act using not just light, but also the most elusive cosmic messengers, gravitational waves and neutrinos. The logic behind this search is powerful. If FRBs are truly the result of the most violent events in the universe, like the cataclysmic merger of two neutron stars, then the incredible energies involved should shake the very fabric of space-time, sending out ripples known as gravitational waves. Similarly, if the bursts are powered by processes that involve collisions of protons or atomic nuclei, so-called hadronic processes, they should be factories for high-energy neutrinos, those ghostly particles that can pass through entire planets without a single interaction. Detecting an FRB alongside a gravitational wave signal or a neutrino flash would be the ultimate confirmation, providing a complete picture of the explosion from multiple, independent perspectives. The process is a breathtaking feat of international scientific coordination. When a radio telescope like CHIME or ASCAP detects a burst, an automated alert rockets across the globe within seconds to networks like the International Gravitational Wave Observatory or LIGO Virgo Cagra collaboration, and to neutrino detectors like IceCube, a gigantic telescope buried deep in the Antarctic ice. These facilities immediately scan their data from the precise moment the FRB was detected, searching for any coincident signal coming from the same general direction in the sky. For a gravitational wave, they would be looking for the characteristic chirp of two massive objects spiraling together. For a neutrino, they would search for a single high-energy particle that arrived at the same time as the radio flash. Finding such a coincidence would be like hearing the thunderclap of an explosion at the exact instant you see the lightning bolt, confirming both the timing and the immense power of the event. Despite years of meticulous searching across hundreds of FRB events, the results have been, for the most part, a profound silence. The hoped-for associations with gravitational waves or neutrino bursts have not materialized. This absence of a multi-messenger signal is not a failure. In science, a null result is itself a powerful piece of data. It places incredibly stringent limits on the nature of the FRB progenitors. The fact that we do not see gravitational waves coincident with FRBs strongly suggests that the one-off bursts are not caused by the inspiral and merger of two neutron stars, at least not of the type we have observed so far. The gravitational wave signal from such a merger is unmistakable and would have been easily detected by LIGO Virgo for an event within a few 100 million light-years. The continuous non-detection forces us to consider that if mergers are involved, they must be happening at distances too far for our current gravitational wave detectors to sense, or they must involve objects with masses or properties that produce a much weaker spacetime ripple. Similarly, the lack of coincident neutrinos is equally telling. Neutrinos are only produced in large numbers when protons or other hadrons are accelerated to extreme energies and then collide with surrounding matter or radiation. The fact that neutrino detectors like IceCube have not seen any excess neutrinos linked to FRBs implies that these bursts are not prolific proton accelerators. This points strongly toward models where the energy is channeled almost exclusively into electrons and their antimatter counterparts, positrons. The leading mechanisms, like the coherent emission from bunches of electrons moving along magnetic field lines, are what physicists call leptonic processes. They are incredibly efficient at producing brilliant radio waves, but are not expected to generate a significant flux of neutrinos. The multi-messenger silence, therefore, is actively steering us away from models involving hadronic cosmic rays and toward those that rely on purely electromagnetic or leptonic physics. It suggests that the engine behind an FRB is a specialist in radio wave production, an artist that works with the brush of electrons and magnetic fields, rather than a messy, all-spectrum explosion that throws every kind of particle and wave into the cosmos. Just when we thought we had categorized the repeating fast radio bursts, the universe presented us with an object that defied even those growing classifications. Enter FRB 1905-20b, a discovery that has become a cornerstone case study, not just for what it bursts, but for what lingers quietly in the silence between those brilliant flashes. This source, found in a dwarf galaxy about 3 billion light-years away, is one of the most active repeaters we have ever seen, firing off bursts with a frequency that makes it a favorite target for astronomers. But its true distinction lies in a companion phenomenon that sets it apart, a persistent radio source or PRS. Alongside the violent millisecond flashes, there is a constant, steady glow of radio emission emanating from the exact same point in the sky. It's as if we've found a cosmic bonfire that not only shoots off spectacular sparks, but also maintains a continuous, smoldering ember at its heart. This persistent glow is not merely background noise. It is a significant and steady source of radio waves in its own right. To put it in perspective, the energy emitted by this persistent source over a single day dwarfs the total energy released in even the brightest single burst. It's a constant, low-level hum of power that is always present, a telltale sign that the environment around this FRB is in a permanent state of extreme activity. The existence of this PRS immediately forged a powerful link to the original repeater, FRB 121102, which was also found to have a similar persistent radio source. Finding two such objects with this dual nature strongly suggests that this is not a fluke but a fundamental characteristic of a specific type of FRB engine. The most compelling explanation is that we are looking at a young, hyperactive magnetar still nestled within the dense nebula created by its own violent birth. Imagine a magnetar as a powerful cosmic engine, and the persistent radio source as the exhaust fumes from that engine, constantly billowing out into space. The leading theory posits that this steady glow comes from a magnetar wind nebula. In this scenario, the rapidly spinning, highly magnetic neutron star is continuously blowing out a relentless wind of charged particles. This wind, traveling at near light speeds, slams into the slower-moving debris left over from the supernova that formed the magnetar. The collision creates a gigantic, expanding bubble of hot, magnetized plasma that is continuously energized. The electrons within this nebula, as they spiral along the magnetic field lines, emit synchrotron radiation, a steady stream of radio waves that we detect as the persistent source. The brilliant FRB flashes, then, could be interpreted as occasional, more violent eruptions from the central magnetar superflares that punch through this nebula, their radio waves amplified or shaped by the surrounding turmoil. This elegant picture, however, immediately raises a new and equally profound mystery. Why do some repeaters, like FRB 1905-20b and 121102, have this prominent persistent radio source, while others, such as FRB 1809-16, the one with the 16-day period, show no such steady glow at all? This discrepancy is a critical clue, hinting at an evolutionary sequence or different environmental conditions. The presence of a strong PRS seems to be a hallmark of youth. A magnetar born from a recent supernova would be surrounded by a dense, massive shell of ejecta, providing the perfect material for its wind to collide with and create a bright, persistent nebula. Over thousands of years, as the nebula expands and dissipates into the wider interstellar medium, this radio glow would gradually fade away. In this view, FRB 1905-20b represents a toddler magnetar, still in its cosmic crib, while a repeater without a PRS might be a more mature, older object whose birth cloud has long since drifted away. The absence of a PRS could also be a matter of geometry and beaming. The persistent nebula might be there, but its emission could be spread out over a wider area, making it too faint for our current telescopes to detect from billions of light-years away. Alternatively, the nebula's emission might be intrinsically weaker if the central magnetar has a less powerful wind, or if it is located in a more barren environment with less surrounding material to interact with. The case of FRB 1905-20b, with its incredibly bright and compact persistent source, therefore offers a pristine laboratory. By studying the relationship between the properties of the bursts and the steady hum of the nebula, how they vary in relation to each other, astronomers can begin to understand the feedback loop between the central engine and its environment. This singular object forces us to consider that the story of a fast radio burst is not just about a momentary explosion, but about the entire life cycle of some of the most dynamic and powerful objects in the universe, from their tumultuous infancy to their potentially quieter old age. But just as we begin to map the cosmic neighborhoods of these bursts, a profound and unsettling discovery throws a wrench into our carefully constructed picture. We call this the dark FRB mystery, and it stands as one of the most perplexing challenges in the field. Imagine astronomers, after years of effort, successfully triangulating the position of a brilliant fast radio burst with pinpoint accuracy. They immediately command the world's most powerful optical telescopes like Hubble or the Keck Observatory to stare at that exact spot, expecting to find the faint, smudge-like host galaxy responsible for the explosion. But when the image comes back, there is nothing. Not a single star, not a hint of a galaxy, just the inky blackness of empty space. This isn't a case of a faint galaxy. This is a complete non-detection, an FRB that appears to have come from a cosmic void, a place where no galaxy should reasonably exist. It's like tracing a phone call to a precise set of coordinates, only to find an empty field with no house, no phone lines, nothing at all. The immediate and most tempting explanation is that the host galaxy is simply too faint for our current telescopes to see. While our optical and infrared observatories are incredibly powerful, they do have a detection threshold. There exists a population of ultra-diffuse galaxies, ghostly collections of stars that are so spread out they have a very low surface brightness, making them incredibly difficult to detect across billions of light years. Alternatively, the galaxy could be shrouded in immense clouds of cosmic dust. Dust particles are excellent at absorbing visible light, effectively rendering a galaxy invisible to optical telescopes. However, that same dust glows brightly in the infrared part of the spectrum. So, when an FRB is localized to a seemingly empty patch of sky, the next step is to point infrared telescopes like the James Webb Space Telescope at the location. If a dusty galaxy is hiding there, Webb's infrared eyes should be able to see through the veil and reveal the hidden stellar metropolis. A non-detection even in the infrared would make the mystery far deeper, forcing us to consider more exotic possibilities. One such possibility is that the FRB source isn't in a galaxy's main disk at all, but has been flung out into the remote dark halo. How could such a thing happen? The answer lies in the violent births of the objects we suspect are responsible. When a massive star goes supernova, the explosion is not always perfectly symmetrical. A slight imbalance can give the resulting neutron star a powerful kick, launching it away from its birthplace at speeds of hundreds of kilometers per second. Over millions of years, this high-velocity neutron star could travel far beyond the visible boundaries of its host galaxy, out into the vast, sparse halo of dark matter and old stars that surrounds it. From our distant vantage point, the faint glow of the main galaxy might be detectable, but the FRB itself would be localized to a point far out in the apparently empty space around it. This scenario paints a poignant picture, a stellar corpse ejected from its home, occasionally flashing its powerful beacon from the cosmic darkness of intergalactic space. But what if the kick was so powerful that the neutron star wasn't just sent to the halo, but was ejected from its galaxy entirely? This is not science fiction. We have observed such hypervelocity stars being flung out of the Milky Way by gravitational interactions with the supermassive black hole at our galactic center. A neutron star receiving a similar kick could achieve escape velocity, becoming a true intergalactic wanderer. It would spend the rest of its life drifting in the immense, empty voids between galaxies. If this object were a magnetar and it produced an FRB, we would localize the signal to a point in the deep void, with no visible galaxy for billions of light years in any direction. This would be the ultimate lonely cosmic lighthouse, a flash from the abyss itself. The probability of detecting such an event is low, given the vast emptiness of intergalactic space, but it remains a theoretically valid and haunting explanation for the darkest FRBs. These dark bursts force a fundamental re-evaluation of where FRB progenitors can live. Our natural assumption is that such powerful events must be tied to regions of active star formation, within the bustling galactic disks where massive stars are born and die. The dark FRB mystery challenges this notion head-on, suggesting that a significant population of these engines might exist in the dim, forgotten outskirts of galaxies or as solitary nomads in the void. This expands the possible habitats for FRBs from the bright city centers of the cosmos to the dark countryside, and even the empty highways between metropolitan areas. Each dark FRB detection is a crucial data point, pushing our telescopes to their absolute limits and compelling us to think creatively about the life stories of these extreme objects. They remind us that the universe still holds profound surprises, and that sometimes the most revealing signals come not from the bright hubs of activity, but from the deepest and most unexpected silences. Now, if we shift our perspective from the unique characteristics of individual bursts to the colossal population as a whole, we encounter a mystery that operates on a grand statistical scale. This is the puzzle of the energy distribution, a concept astronomers refer to as the log and log-s relation. At its heart, it's a surprisingly simple question. In any given patch of sky, how many faint, fast radio bursts are there for every incredibly bright one? You might intuitively guess that the fainter something is, the more common it should be. After all, in a dark room, you're far more likely to see a few distant, dim candles than a single blinding spotlight. This intuitive relationship holds a profound mathematical truth that can reveal whether we are looking at a local population of objects or one that stretches across the expanding universe. To understand this, imagine a perfectly static, infinite universe that doesn't expand, what cosmologists call a Euclidean universe. In this simplified cosmos, the number of sources you can see increases with the cube of the distance. But there's a catch: the brightness of a source fades with the square of the distance. When you combine these two effects, you get a very specific, predictable relationship. If you make a graph where one axis is the logarithm of the burst's flux, or how bright it appears to us, and the other axis is the logarithm of the number of bursts that are at least that bright, the data points should fall along a straight line with a specific slope, in this case, a slope of -1.5. This log n log s curve is like a cosmic ruler. If the bursts we detect follow this Euclidean slope, it would suggest we are seeing a population of objects that is uniformly distributed in a relatively local volume of space. However, when astronomers plot the data from powerful surveys like CHIME, which has detected thousands of bursts, the observed distribution clearly veers away from this simple Euclidean prediction. The line of data points is significantly flatter. There are fewer faint bursts than the simple model would expect. This deviation is not an error, it's a crucial signal. It tells us that we are not living in a static universe. The faintest bursts are the ones that have traveled the farthest to reach us, and the expansion of the universe itself is stretching their radio waves to lower frequencies, and more importantly, diluting their apparent brightness over the vast cosmic distances. This cosmological effect, combined with the fact that the universe was different in the past, perhaps with more or fewer FRB progenitors, flattens the log n log s curve. The observed distribution is therefore a powerful confirmation that fast radio bursts are indeed cosmological, originating from billions of light years away, their numbers and apparent strength shaped by the history of cosmic expansion. This flattened curve is far more than just a confirmation of distance. It is a critical key to unlocking the intrinsic properties of the FRB sources themselves. By carefully measuring how the observed distribution deviates from the simple Euclidean expectation, astronomers can work backwards to determine the luminosity function. This function describes the true, underlying diversity of the cosmic engines. Are most FRB sources relatively modest, with only a few rare monsters capable of producing the incredible galaxy outshining flashes? Or is there a continuous spectrum of power? The data suggests that less energetic bursts are vastly more common than the extremely energetic ones. This makes intuitive sense. It's like earthquakes, where small tremors are frequent, but massive, civilization-shaking quakes are rare. This luminosity function places severe constraints on theoretical models. It tells us that any successful model for FRB progenitors must be able to explain why the engines produce a wide range of energies and why the weaker events are the dominant population throughout cosmic history. Ultimately, the log n log s relation transforms fast radio bursts from a collection of individual mysteries into a unified statistical sample. Each new burst detected is not just another data point. It's another vote in a cosmic election that is helping us determine the life cycle of these objects across the age of the universe. Are they more prolific in the early universe, when galaxies were younger and forming stars more rapidly? Or do they occur at a steady rate? The evolving slope of this distribution at different distances holds the answer. By reading this statistical signature, we are no longer just studying the bursts themselves, but using them as tracers to map the evolution of cosmic violence over billions of years, turning their random flashes into an ordered history of power and time. Just when we thought we had a handle on the environments surrounding these bursts, the universe presented a new, dynamic puzzle that revealed the magnetic chaos right next to the source. We've already explored how Faraday rotation twists the polarization of radio waves, acting as a probe for magnetic fields along the line of sight. But for one repeater in particular, this measurement became a roller coaster. Astronomers monitoring FRB 121102 discovered that its rotation measure wasn't just high, it was wildly unstable, changing dramatically over just a few months and even flipping its sign entirely. This meant that the magnetic field through which the bursts were traveling wasn't just powerful and ordered, it was in a state of violent, real-time flux. The environment around this object wasn't a static backdrop, it was a seething, evolving storm. To understand the significance of this, picture the rotation measure as a cosmic dial that measures both the strength and the direction of a magnetic field along our line of sight. A positive value indicates a field pointing more or less toward us, while a negative value means it's pointing away. A stable, high rotation measure points to a consistent, powerful magnetic environment. But a rotation measure that swings from a large positive number to a large negative number, as it did for 121102, is like watching a compass needle spin erratically. This can only happen if the magnetic field in the plasma surrounding the source is itself reversing direction. Such a dramatic change implies that the material around the FRB engine is not just sitting there, it is moving at tremendous speeds, perhaps being churned by powerful winds or shocked by repeated eruptions from the central object. The magnetic field lines themselves are being stretched, twisted, and tangled in this cosmic blender. This incredible variability provides an unprecedented, real-time window into the heart of a magnetar's cradle. The most compelling explanation is that we are witnessing the dynamics of a young, hyperactive magnetar wind nebula. In this scenario, the magnetar is continuously blowing a fierce wind of charged particles, which slams into the slower-moving debris from the supernova that created it. This creates a turbulent bubble of hot, magnetized plasma. Each time the magnetar unleashes a giant flare or an FRB, it injects more energy into this nebula, shocking the plasma and stirring the magnetic field. The observed changes in rotation measure could be due to our line of sight passing through different, rapidly evolving filaments within this nebula. 1 month, we might be looking through a region where the magnetic field is dominated by a structure pointing toward us. The next, a powerful shock wave or a new ejection of material could have reconfigured the field, making it point away. It's like watching the churning pattern in a boiling pot of water, but on a scale of light years and with magnetic fields strong enough to tear atoms apart. The fact that this is happening on human timescales over months and years is what makes it so astonishing. In astronomy, we are used to processes that unfold over millions of years. To see such profound changes in a fundamental property like a magnetic field orientation in what amounts to a cosmic instant tells us that the environment around this FRB is exceptionally young and dynamic. It strongly supports the idea that FRB 121102 is a very newborn magnetar, perhaps only decades or centuries old, still surrounded by the intensely chaotic and expanding remnant of its own violent birth. The variable rotation measure is therefore more than just a curious observation. It is a direct measurement of the growth and evolution of a cosmic engine's immediate surroundings, offering a glimpse into the turbulent adolescence of one of the universe's most extreme objects. This intricate dance of radio waves with their surroundings is crucial, but to truly understand the story each burst is telling, we need to zoom in to the most immediate environment of all. This brings us to the circumstellar medium puzzle, the complex shell of material that represents the final frontier between the central engine and the vastness of space. Think of the journey of an FRB's radio waves not as a simple sprint across the universe, but as a dramatic escape from a fortified castle. Before the signal can even begin its billion-year voyage, it must first navigate a dense, turbulent, and incredibly magnetized maze of plasma right next to the source. This local environment, known as the circumstellar medium or CSM, is the crucible where the burst's final character is forged, imprinting clues about the recent life and violent death of the progenitor star. The fingerprints of this circumstellar medium are all over the signal we receive. The three key properties we've discussed, scattering, dispersion measure, and Faraday rotation, are not just shaped by the long journey through intergalactic space. They are dramatically amplified by this local screen of material. For instance, the extreme scattering that stretches a millisecond burst into a longer, smeared-out signal is a direct consequence of the radio waves encountering a clumpy, turbulent plasma. The incredible Faraday rotation, which twists the polarization of the waves, demands a magnetic field of immense strength and coherence. These effects are so pronounced in some FRBs that they cannot be explained by the diffuse gas between galaxies alone. They point unequivocally to a dense, complex, and intensely magnetized environment sitting light days or light weeks away from the central engine. It's like trying to hear a whisper from inside a roaring hurricane. The storm closest to the source has the greatest effect on the message. So, what is the nature of this cosmic hurricane? The leading theory paints a vivid picture of stellar death and rebirth. Imagine a massive star, many times heavier than our Sun, approaching the end of its life. In its final millennia, it becomes unstable, undergoing violent convulsions that eject huge amounts of its own atmosphere into space. This material forms a dense, expanding shell of gas and plasma surrounding the dying star. Then the star's core collapses, triggering a supernova explosion. The outer layers are blasted away, but the innermost part of that previously ejected shell can survive, forming a dense circumstellar nebula. At the heart of this nebula, the collapsed core becomes a neutron star, often a highly magnetic magnetar. This newborn magnetar is now cocooned within the debris of its own violent birth, a circumstellar medium rich with material and threaded with the magnetic field of the original star, now amplified and tangled by the explosion. This model elegantly explains the observed characteristics. The dense plasma in this circumstellar shell is responsible for the extra dispersion and intense scattering. The powerful, ordered magnetic fields frozen into this ejected material cause the extreme Faraday rotation. The variations in these properties from one burst to the next simply reflect differences in the mass, density, and age of this surrounding nebula. A younger magnetar would be enshrouded in a thicker, more turbulent CSM, leading to heavily scattered and distorted bursts. An older magnetar, whose birth cloud has had time to expand and dissipate, would allow cleaner, sharper signals to escape. In this way, analyzing an FRB is like using a sophisticated form of cosmic sonar. Each burst acts as a ping that echoes through the circumstellar medium. By meticulously measuring the delay, the smearing, and the twisting of the returning echo, astronomers can effectively map the structure, density, and magnetic field of this otherwise invisible material. They can determine if the progenitor star shed its material in a steady wind or in violent, episodic eruptions, piecing together the final chapters of a star's life from the environment its death created. The circumstellar medium is therefore not just an obstacle for the radio waves. It is a precious archive, preserving a record of the events that led to the creation of one of the universe's most enigmatic engines. Given that magnetars, the leading suspects for many fast radio bursts, are the collapsed cores of massive stars that have exploded as supernova, it seems almost inevitable that we should find these brilliant radio flashes nestled within the glowing, expanding shells of their own birth clouds. It's a logical chain. A massive star lives a short, violent life and ends it in a core collapse supernova. If the core is heavy enough, it becomes a neutron star, potentially a highly magnetic magnetar, and that magnetar then produces FRBs. Therefore, when we pinpoint an FRB to its host galaxy, we should see a young supernova remnant, a brilliant nebula of ejected gas, shining brightly at the same location. This expectation sets up one of the more subtle yet persistent mysteries, the surprising absence of a clear, consistent supernova connection. The case of the original repeater, FRB 121102, is particularly telling. This source is located in a tiny, rambunctious dwarf galaxy that is a hotbed of star formation. This environment is exactly where you would expect to find recent supernova. It's a stellar nursery where massive stars are being born and dying in rapid succession. Yet, when astronomers pointed the Hubble Space Telescope and other powerful instruments at the precise location of the FRB, they found no evidence of a bright, young supernova remnant. There is star-forming gas and the general glow of a busy galaxy, but no distinct circular shell of ejected material that would mark the recent explosive death of a star. This is a profound puzzle. If a magnetar is powering these repeated bursts, and magnetars are young objects thought to be highly active for only the first few thousand to tens of thousands of years of their lives, then the supernova remnant from its birth should still be there, glowing brightly for all to see. Its absence forces us to reconsider the timeline or the very nature of the progenitor. So, where did the supernova remnant go? Several intriguing possibilities emerge. The first is simply a matter of time. Perhaps the supernova that created the magnetar happened longer ago than we typically assume. A supernova remnant is a brilliant but relatively short-lived phenomenon. The expanding shell of gas initially glows brightly as it rams into the surrounding interstellar medium. But after several tens of thousands of years, it expands and dissipates to the point where it becomes too faint and diffused to detect from a distance of billions of light years. It's possible that the magnetar at the heart of FRB 121102 is not a newborn, but a more mature object, perhaps several tens of thousands of years old. Its remnant has simply faded from view, leaving behind the still active magnetar to continue its flaring life. This would imply that magnetars can remain potent FRB engines for far longer than our simple models suggest. Another possibility is that the supernova itself was an unusual, underachieving event. Not all stellar explosions are created equal. Some core collapse supernova are exceptionally faint, perhaps because a large amount of the star's mass falls back onto the newly formed neutron star, robbing the explosion of its energy. In an extreme case, a failed supernova might occur where the star collapses directly into a black hole with only a feeble optical outburst. If the magnetar was born in such a whimper rather than a bang, the resulting supernova remnant would be exceptionally dim and difficult to spot, potentially explaining its absence in our deep images. The birth of the engine in this scenario was a quiet, stealthy affair, leaving behind a powerful object without the customary brilliant funeral shroud. A third, and perhaps most fascinating, idea introduces a significant delay between the supernova and the onset of FRB activity. What if a magnetar doesn't start producing these brilliant radio bursts immediately after it is born? Its youth might be dominated by different types of activity, such as giant X-ray and gamma-ray flares, as it settles into its new identity. The FRB producing mechanism might only switch on later, once the magnetar's magnetic field has evolved to a certain configuration, or once the dense birth cloud around it has cleared enough for the radio waves to escape efficiently. In this view, by the time the magnetar begins its career as an FRB source, its supernova remnant has already significantly faded. The lack of a coincident remnant isn't an anomaly, it's the expected signature of an engine that takes thousands of years to warm up. This reframes the FRB not as a birth cry, but as a distinct phase in the long life of a magnetar. The absence of a clear supernova connection, therefore, is not a dead end but a critical clue, pushing us to think more deeply about the life cycle of these extreme objects and the varied ways in which a star can die and leave behind a legacy of cosmic violence. But the story of a fast radio burst journey is told not just in its timing or its polarization, but also in its very shape. When astronomers compare the same burst as it appears across different radio frequencies, a subtle yet revealing pattern often emerges. The pulse, which might be a sharp, needle-like spike at high frequencies, can appear noticeably broader and more rounded at the lower end of the dial. It's as if the burst has been stretched out, its crisp edges softened into a gradual rise and fall. This frequency-dependent broadening is a direct fingerprint of the cosmic terrain the signal has traversed, and it points to a specific physical process known as scattering. The culprit behind this smearing effect is the turbulent sea of ionized gas or plasma that fills the space between stars and galaxies. This isn't a smooth, homogeneous medium. It's filled with microscopic clumps and density fluctuations like countless tiny lenses floating in space. As the radio waves from an FRB pass through this turbulent fog, they don't all take a straight path. Instead, they are deflected by these tiny irregularities, scattering onto slightly different routes. Here's the crucial part: this scattering is far more effective at longer wavelengths. Lower frequency radio waves are more easily pushed off course by these small-scale plasma clouds than their higher frequency counterparts. The result is that the lower frequency components of the burst arrive at our telescopes after taking a more scenic, delayed route. Instead of all the light from the burst arriving at the same instant, the lower frequencies get smeared out over a longer period, creating that characteristic broadening effect. It's analogous to how red light penetrates fog better than blue light, but in reverse, for radio waves, it's the high-frequency, blue light that punches through more directly. This phenomenon is so predictable that astronomers have turned it into a precise diagnostic tool. By carefully measuring how much wider a burst appears at a low frequency like 400 MHz compared to a high frequency like 2 GHz, they can calculate what's known as the scattering measure. This measure quantifies the total amount of turbulent plasma the signal encountered along its entire path. A heavily scattered burst with a pulse that is stretched over many milliseconds indicates a journey through a particularly dense and chaotic plasma environment. This often suggests the burst originated in a messy region, like the heart of a star-forming nebula or deep within the chaotic disk of its host galaxy. Conversely, a burst that shows very little scattering, arriving as a sharp spike even at low frequencies, indicates an remarkably clean line of sight, perhaps one that passed through the quieter, more diffuse outskirts of galaxies or through a vast intergalactic void. This is where the mystery deepens. While many bursts show the expected strong scattering, others defy this expectation. Some FRBs, even those localized to distant galaxies, arrive with surprisingly narrow pulses across a wide range of frequencies. This tells us that their journey was extraordinarily clean, with minimal turbulent plasma to scatter their signal. How can a burst travel billions of light years and still remain so pristine? It suggests that the large-scale structure of the universe is not uniformly frothy. There must be vast corridors of space that are exceptionally calm and smooth, great cosmic voids where the plasma is so tenuous and undisturbed that it barely affects the passing radio waves. These clean sight lines are just as informative as the cluttered ones. They allow astronomers to isolate and study the dispersion and other effects caused solely by the intergalactic medium itself, without the complicating factor of scattering. By cataloging the scattering measures of hundreds of bursts, we are effectively creating a weather map of the cosmos, charting the stormy plasma fronts and the calm, clear stretches that define the invisible architecture of the universe. Each burst's width becomes a delicate probe, measuring the microscopic texture of the space it has crossed. The discovery of a 16-day period in one repeater was a landmark moment, proving that some of these cosmic engines operate on a precise, predictable clock. But this immediately raised a tantalizing question for astronomers. Is this the rule or a magnificent exception? Is periodicity a common feature hidden within the seemingly random chatter of other repeating FRBs, waiting to be discovered with more careful analysis? This launched an intensive, data-driven treasure hunt, a meticulous search for hidden rhythms in the cosmic noise, using some of the most powerful statistical tools in the astronomer's arsenal. The primary weapon in this hunt is a mathematical technique called Fourier analysis. In simple terms, this method allows scientists to take a messy, irregular signal, like the arrival times of bursts from a repeater over many months or years, and break it down into a spectrum of simpler, repeating sine waves. It's like listening to a complex chord of music and using a filter to isolate the individual notes that make it up. Astronomers apply this to the timeline of an FRB's bursts, searching for a dominant frequency that stands out above the random background. If such a frequency is found, it reveals a hidden periodicity, a regular beat underlying the apparent chaos. For unevenly spaced data, which is common in astronomy due to telescope scheduling and weather, a related method called the Lomskagel periodogram is often used. This powerful algorithm is specifically designed to find periodic signals in observations that are taken at irregular intervals, making it perfect for analyzing the stop and start data from FRB monitoring campaigns. The implications of finding a second or even a third repeating FRB with a clear period would be enormous. It would strongly suggest that a binary system is a common, perhaps even fundamental, configuration for these objects. Each new period would give us a new set of orbital parameters to study: the mass of the companion, the shape of the orbit, the distance between the stars. We could begin to build a taxonomy of FRB binary systems, classifying them by their orbital periods and trying to link those periods to the properties of their bursts. Does a shorter orbital period correlate with more energetic flares? Does the active window, the part of the orbit when bursts are emitted, change depending on the nature of the companion star? Finding multiple periodic sources would transform the field from studying individual curiosities to understanding a population with shared physical laws. Conversely, the failure to find clear periods in other repeaters is equally significant. If most repeating FRBs show no evidence of a strict clock, even after years of observation, it points toward a different kind of triggering mechanism altogether. Instead of a predictable orbital dance, the bursts might be driven by internal processes that are inherently more chaotic. Think of it like the difference between a geyser and an earthquake. A geyser, driven by subsurface heat and pressure, erupts on a semi-regular schedule. An earthquake, however, is the result of stress building up along a fault line until it suddenly and unpredictably releases. If FRBs lack periodicity, their engine might be more like a seismic event on a neutron star. The trigger could be a starquake, where the incredible strain on the magnetars crust, a crust 10 billion times stronger than steel, builds up until it catastrophically fractures. Or it could be a magnetic reconnection event, where the star's immensely powerful magnetic field lines become so twisted that they snap and reconfigure themselves, releasing their stored energy in a violent flash. These processes can be influenced by a slow buildup of stress, making them somewhat episodic, but not locked into a precise external clock like an orbit. This search for periodicity is not a simple yes or no endeavor. Some sources might exhibit quasi-periodicity, where there is a rough, statistical tendency for bursts to cluster around certain times, but without the rigid precision of the 16-day source. This gray area could indicate a more complex system. Perhaps the neutron star is in a wide, eccentric orbit that makes the timing less exact. Or maybe the period we see is not from the orbit itself, but from the slower precession of the neutron star's spin axis, a wobble that changes the direction of the radio beam over a longer, more variable timescale. The intensive, ongoing analysis of every known repeater is therefore a process of peeling back layers of complexity, trying to distinguish a clean orbital signal from the noisy, internal dynamics of a supremely violent object. Each new data point, each new burst recorded, adds another piece to the puzzle, helping us determine whether these cosmic lighthouses are guided by the stately clockwork of orbital mechanics or the unpredictable tremors of a star under unimaginable stress. Just when we thought we had witnessed the peak of repeating FRB activity, the universe unveiled a spectacle that dwarfed all previous records, an object that redefined what it means to be active. This is the story of FRB 2020-1124a, a source that didn't just repeat, it erupted in a veritable storm of cosmic violence, a frenzy of flashes that earned it the memorable nickname of the Christmas tree burster. For a breathtaking 54-hour period in September of 2021, this single object unleashed a staggering total of 1,863 distinct bursts. At its peak, it was firing off brilliant millisecond flashes more than once per minute, a rate of activity so intense it provided a data set larger than all other known repeaters combined. It was as if a cosmic dam had burst, allowing astronomers an unprecedented front-row seat to the inner workings of one of the universe's most powerful engines. The sheer volume of data from this outburst was a statistician's dream and a theorist's playground. Unlike other repeaters that might offer a handful of bursts over months of patient waiting, the Christmas tree burster delivered a continuous fire hose of information. This allowed scientists to perform analyses that were previously impossible. They could study the distribution of energies in exquisite detail, revealing that the source produced everything from faint whispers to colossal, galaxy-outshining roars, all within the same active phase. They could analyze the fine-scale structure of individual bursts, finding the now familiar downward drifting sub-pulses in abundance, but also discovering new, more complex patterns that hinted at a highly dynamic and turbulent emission region. This storm was not just a louder version of what we'd seen before, it was a qualitative leap offering a high-definition view of the chaos. When astronomers succeeded in pinpointing the home of this remarkable object, the result added another layer of intrigue. FRB 2020-1124 was localized to a massive, barred spiral galaxy, a grand design galaxy much like our own Milky Way, located about 1.3 billion light-years away. This was significant because it stood in stark contrast to the first known repeater, FRB 121102, which resided in a tiny, metal-poor dwarf galaxy. The Christmas tree burster was living in a cosmic metropolis, a mature, well-ordered galaxy, proving that these powerful engines are not confined to one type of galactic environment. They can ignite in the frantic stellar nurseries of small galaxies and within the more settled neighborhoods of large spirals, suggesting the underlying progenitor is a versatile and widespread phenomenon. But the most startling clue came from measuring the polarization of its radio waves. Just like with FRB 121102, astronomers detected an extreme and wildly variable Faraday rotation. The magnetic field along the line of sight was not only incredibly powerful but also in a state of rapid flux, changing significantly over a matter of days. This wasn't just a turbulent environment, it was an environment undergoing a dramatic transformation in real time. The fact that this extreme variability was happening concurrently with the most prolific bursting activity ever observed was almost certainly not a coincidence. It painted a picture of a central engine whose local surroundings were being violently reshaped, with the bursts themselves likely being both a symptom and a cause of the upheaval. This leads to the central mystery of the Christmas tree burster. What flips the switch on such an incredible active state? What triggers a magnetar, or whatever engine is at the heart of this, to transition from a period of relative quiet to a feverish pitch of eruption? Scientists are exploring two broad categories of triggers, external and internal. An external trigger could involve a foreign body, like an asteroid or a comet, being torn apart by the magnetar's immense gravity. If a large chunk of rocky or metallic material were to venture too close, the tidal forces would shred it into a disk of debris around the neutron star. As this material then rains down onto the magnetar's surface, it could ignite a chain reaction of explosions, each impact triggering a release of magnetic energy that manifests as an FRB. This model elegantly explains the storm-like nature of the activity. A single disruptive event leads to a cascade of bursts as the infalling material is consumed. The alternative is an internal trigger rooted in the innate instability of the magnetar itself. The interior of a neutron star is a realm of bizarre physics where a superfluid core rotates independently of a solid crystalline crust. The magnetic field anchored to this crust is under unimaginable stress. It's possible that the system simply reaches a tipping point. The stresses build up until the crust can no longer contain them, leading to a major starquake. This fracture wouldn't be a single event but could set off an avalanche of smaller quakes and magnetic reconnections across the star's surface, like tectonic plates shifting after a major earthquake, releasing the pent-up energy in a spectacular series of bursts. The observed changes in the Faraday rotation could then be a direct consequence of this global reconfiguration of the star's magnetic field, with the ejected plasma from the eruptions altering the environment immediately around the source. The incredible activity of FRB 2020-1124 provides compelling evidence for both ideas. The storm-like cluster of bursts, with its rapid onset and gradual decline, fits the picture of a single cataclysmic external event. However, the complex, evolving structure of the individual bursts and the dramatic changes in the local magnetic field point strongly toward intricate internal processes. The most likely scenario is a combination of the two. The magnetar's internal instability creates a predisposition for an active phase, and an external catalyst like the infall of material provides the final nudge that pushes the system over the edge. The Christmas tree burster, in all its glorious complexity, shows us that these cosmic engines are not simple on-off switches. They are complex systems where internal dynamics and external influences intertwine, capable of building toward moments of spectacular fury that illuminate the darkest corners of the cosmos with their frantic, brilliant light. But to truly listen to the story a fast radio burst is telling, we need to pay attention not just to its loudness or its timing, but to its very essence, the specific way its radio waves vibrate as they travel through space. This brings us to the subtle yet profoundly revealing mystery of polarization. If you think of a radio wave as a rope being shaken, polarization describes the direction in which that rope is vibrating. Is it moving up and down, side to side, or in a more complex pattern? For FRB, the answer to this question is a direct message about the magnetic environments they have encountered, acting as a built-in cosmic compass that has recorded its journey. The vast majority of fast radio bursts exhibit a high degree of linear polarization. This means the radio waves are vibrating predominantly in a single, well-defined plane, like a rope being shaken strictly vertically or horizontally. This is a crucial clue. For light to become highly polarized, it must either be emitted in a highly organized way, or it must pass through a region with a strong, uniform magnetic field that filters and aligns the vibrations. The high linear polarization seen in FRBs strongly suggests that the emission process itself is what astronomers call coherent. Instead of being generated by the random, chaotic motion of particles, the radio waves are produced by trillions of electrons moving in perfect synchrony, like a well-rehearsed orchestra playing a single pure note. This coherent emission naturally results in waves that are perfectly in step, vibrating in an orderly fashion. Furthermore, the survival of this linear polarization across billions of light years indicates that the burst has traveled through a relatively clean, magnetically smooth environment. If it had passed through a highly turbulent Faraday rotating screen, the polarization angle would have been scrambled, randomizing the signal. The fact that it remains so ordered tells us that the path, at least on large scales, is not dominated by chaotic magnetic fields. However, the plot thickens when we detect significant circular polarization in a burst. In this case, the electric field of the radio wave doesn't just oscillate in a plane. It actually rotates as the wave travels, tracing out a corkscrew or helical path through space. This signature can arise in two main ways. First, it can be an intrinsic property of the emission mechanism at the source. Certain plasma physics processes, known as plasma modes, can naturally generate circularly polarized waves. For example, if the emission is generated in a region where electrons are gyrating around magnetic field lines, the resulting radiation can be circularly polarized. The specific handedness of the rotation, whether it corkscrews to the left or the right, can even tell us about the direction of the magnetic field relative to our line of sight. Secondly, circular polarization can be induced during the wave's propagation. As a linearly polarized wave travels through a region of magnetized plasma, it can be converted into a circularly polarized wave through an effect known as Faraday conversion. This is distinct from Faraday rotation, which twists the plane of linear polarization. Faraday conversion actually transforms one type of polarization into another, and it is most effective in dense, magnetized environments. Therefore, detecting circular polarization forces us to ask, are we seeing a fundamental characteristic of the engine itself, or is it a distortion imprinted on the signal by the material it traveled through near the source? The most powerful insights come when we don't just look at the overall polarization of a burst, but when we dissect it millisecond by millisecond across its different frequency components. This time-resolved and frequency-resolved polarization analysis is like putting the burst under a high-powered microscope. For some repeating FRBs, astronomers have observed a fascinating evolution. The degree of linear polarization might change dramatically between different subpulses within a single burst, or the angle of polarization might smoothly rotate as the burst progresses. This is akin to watching a compass needle swing during a storm. Such a dynamic change is incredibly difficult to explain by propagation effects alone. It almost certainly reflects changes happening in real time at the source. If the emission is beamed from a specific region on a spinning neutron star, the rotation of the star itself would cause the polarization angle to sweep over the course of a few milliseconds. Alternatively, if the burst is caused by a propagating shock wave or a series of magnetic reconnection events moving through a complex field structure, the changing polarization would map the geometry of that magnetic field, showing us how it curls and twists in the heart of the explosion. This ability to trace magnetic field geometry is perhaps the most exciting aspect of polarization studies. A burst that maintains a constant, high level of linear polarization throughout its duration suggests a stable, large-scale, and highly ordered magnetic field, like the dipolar field of a classic pulsar. In contrast, a burst that shows a chaotic mix of linear and circular polarization, with angles that jump erratically, points to a much more complex and tangled magnetic environment, perhaps like the multipolar field near the surface of a young, hyperactive magnetar where different magnetic loops are interacting violently. By reading these subtle polarization signatures, we are doing something remarkable. We are remotely sensing the magnetic personality of an object smaller than a city from an impossible distance, using the fleeting imprint it leaves on a radio wave as its only messenger. The polarization of a fast radio burst is therefore far more than a technical detail. It is a rich, complex language that describes the ordered chaos of the most powerful engines in the universe, giving us a direct line into the heart of the magnetic storm. Now, for all their immense power and intricate structure, there is one characteristic of fast radio bursts that arguably poses the most fundamental challenge to physics itself. A number so extreme it pushes against the very limits of what we believe is possible. This is the mystery of the brightness temperature. To understand this, we need to step back from the cosmic scale and think about a simple, everyday concept: temperature. When we say an object is hot, what we mean on a microscopic level is that its atoms and molecules are jiggling around rapidly. The light it gives off, whether it's the red glow of a heating coil or the white-hot intensity of the sun, is a direct result of this random, chaotic thermal motion. We call this thermal emission. Now, astronomers have a way to quantify this. They define a concept called brightness temperature, which is essentially a measure of how bright a radio source would be if it were a simple hot object emitting thermally at a single radio frequency. Here's where the numbers become almost incomprehensible. A typical fast radio burst, when you calculate its brightness temperature, yields a value that can soar beyond 10 to the 35th power Kelvin. To grasp how absurdly large that is, consider that the core of our Sun has a temperature of about 15 million Kelvin. The brightest known quasars, the active hearts of distant galaxies, might reach brightness temperatures of around 10 to the 12th Kelvin. An FRB outshines these by a factor of 10 trillion. This number is so astronomically high that it completely shatters any possibility that the emission is thermal. There is no known or even conceivable physical object that can be that hot. At such temperatures, the particles would have so much energy that they would instantly annihilate each other or collapse into a black hole. The brightness temperature is not a real temperature. It is a convenient but staggering measure of the sheer intensity of the radio emission. This impossible number points to one inescapable conclusion. The radio waves from an FRB are not produced by the random jiggling of hot particles. Instead, they must be generated by a process known as coherent emission. Think of the difference between the light from a light bulb and the light from a laser. A light bulb is an example of incoherent emission. The countless atoms in its filament glow independently, like a crowd of people all talking at once, creating a general, diffuse light. A laser, however, is the epitome of coherence. All the atoms are forced to emit their light waves in perfect lockstep, in phase with one another. The peaks and troughs of the light waves align perfectly, creating an intense, focused beam. The brightness temperature of a laser beam is effectively infinite for this reason. An FRB is the cosmic equivalent of a laser, but operating in the radio part of the spectrum and on a scale that dwarfs human engineering. The particles producing the radio waves, most likely electrons and their antimatter counterparts, positrons, must be acting in a coordinated, synchronized dance, emitting their radiation in phase to create a signal of such concentrated brilliance. The central mystery, then, is not the energy itself, but the mechanism of this coherence. How does nature orchestrate this perfect synchronization on an astrophysical scale? How do you get trillions upon trillions of particles to act as one across a region that could be hundreds of kilometers wide? This is the true heart of the FRB puzzle. The leading theories all try to solve this coordination problem, and they involve some of the most extreme plasma physics imaginable. One prominent idea is the synchrotron maser. We're familiar with lasers that use light. A maser is the same principle but for microwaves or radio waves. In this model, a shock wave plows through a magnetized plasma. The shock energizes the particles, pushing them into a so-called inverted population state, where more particles are in a high-energy state than a low-energy one. This is an unstable situation, ripe for an avalanche. When a radio wave passes through this prepared medium, it stimulates the excited particles to emit more radio waves that are perfectly in phase with the original wave, leading to an exponential amplification of the signal. It's a natural amplifier, creating a coherent blast from a chaotic shock. Another compelling mechanism is coherent curvature radiation. Imagine a bunch of electrons traveling at near light speed along a tightly curved magnetic field line, like a train speeding around a sharp bend. As they are forced to change direction, they emit radiation. If these electrons are packed together into a dense, compact cloud, a bunch, they will each emit a radio wave. Because they are so close together and moving in the same path, these waves will be emitted almost simultaneously and will be in phase with one another, combining to form a powerful, coherent pulse. The challenge is forming and maintaining these bunches in the violent environment around a neutron star, but it's a process that could naturally produce the required coherence on a very short timescale. What makes this so difficult for theorists is that we are trying to model plasma processes that occur in magnetic fields trillions of times stronger than anything we can create in a laboratory, under densities and energies that stretch the laws of physics as we know them. The incredible brightness temperature of fast radio bursts is therefore more than just a record-breaking statistic. It is a direct window into a realm of coordinated, large-scale quantum behavior, forcing us to invent new physics to explain how the universe can create such a perfect, powerful radio laser across billions of light years. For all the challenges of observing at the lowest frequencies, a deeper theoretical puzzle was lurking, one that strikes at the very assumptions we make about the environment right next to the source. This is the mystery of the missing low-frequency cutoff. According to a well-established principle in plasma physics known as synchrotron self-absorption, there should be a fundamental limit to how low an FRB signal can go. Imagine the source of the burst is embedded in a dense, magnetized cloud of its own, making a plasma so thick with energetic particles that it acts like a fog for its own light. At very low radio frequencies, the theory states the plasma should become opaque. The radio waves generated inside this fog would be reabsorbed by the very electrons that are creating them, effectively trapping the energy and preventing it from escaping. It would be like trying to shout through a thick blanket. The sound gets absorbed before it can travel very far. Astrophysicists predicted that this effect would create a sharp cutoff in the spectrum of an FRB. Below a certain critical frequency, the brilliant signal should simply vanish, dropping off a cliff. The predicted location of this cliff is directly tied to the properties of the plasma cocoon. A denser, more magnetized environment would push the cutoff to a higher frequency, meaning the source would be silent across a wider swath of the radio band. A more diffuse environment would allow the signal to extend to lower frequencies. Therefore, finding this cutoff point in an observed FRB would be a powerful way to measure the density and magnetic field strength right at the source. It would act as a precise diagnostic, telling us exactly how thick the cosmic fog is that the radio waves must punch through. For years, this was the expectation, that each FRB would have its own unique low-frequency limit, a fingerprint of its local conditions. The reality, as detected by telescopes like LOFAR and the Giant Meter Wave Radio Telescope, has been a profound surprise. While the signals at low frequencies are indeed heavily scattered and stretched, they are most definitely there. The repeater FRB 121102, for instance, has been detected clearly at frequencies as low as 150 MHz, and there are tantalizing hints of emission even lower. The sharp cutoff predicted by synchrotron self-absorption is conspicuously absent. Instead of falling off a cliff, the signal persists, like a faint but determined voice managing to whisper through that theoretical blanket. This is more than a minor discrepancy, it's a direct challenge to our models. The most straightforward interpretation is that the plasma environment immediately surrounding the FRB engine is far less dense than we assumed. If the plasma is thin enough, the radio waves can escape without being significantly reabsorbed, even at very long wavelengths. This suggests that the emission region might not be deeply buried within a dense nebula, but could be situated in a more evacuated cavity, perhaps cleared out by previous eruptions from the central magnetar. However, a lower density is not the only possible explanation. The absence of a cutoff could also be a clue about the sheer compactness of the emission region itself. The theory of synchrotron self-absorption assumes a certain size for the source. If the region producing the radio waves is incredibly small, even by the already stringent standards of FRB engines, then the conditions for efficient self-absorption might never be met. In this scenario, the radio waves are generated in such a tiny, concentrated volume that they escape before the plasma has a chance to reabsorb them, like a bullet fired from a gun moving too fast to be caught. This would imply an emission region even more compact than a typical neutron star's magnetosphere, perhaps pointing to processes happening on magnetic field lines incredibly close to the star's surface or within a highly confined shock wave. A third, more radical idea involves the very mechanism of the emission. What if the coherent radiation is produced in a way that inherently avoids self-absorption? Some theoretical models suggest that if the emission is generated by a process called a charged bunched beam, where particles are organized into tight clusters, the coherence itself could suppress the absorption effect. The radiation is emitted so efficiently and directly that it bypasses the usual plasma interactions that would cause it to be trapped. The missing low-frequency cutoff, therefore, might not be a puzzle to be solved by adjusting plasma parameters, but a fundamental signature that the emission is occurring via a specific, highly efficient coherent process. Each of these interpretations, a lower density, a more compact source, or a special emission mechanism, forces a significant re-evaluation of the conditions in the heart of the storm. The silence we expected to find at the low end of the radio dial has instead spoken volumes, telling us that the nursery of these cosmic flashes is even more unusual and finely tuned than we had ever imagined. Beyond the grand distortions of scattering and Faraday rotation lies an even finer imprint on the signal, a subtle flickering that transforms the intergalactic medium from a featureless void into a canvas of intricate texture. This phenomenon is known as scintillation, and it acts as a cosmic microscope, allowing astronomers to probe the universe on astonishingly small scales. If scattering is like the blurring of a light seen through a heavy fog, scintillation is the sharp, rapid twinkling of a star in our own night sky, caused by turbulence in Earth's atmosphere. For a fast radio burst, this twinkling is not caused by our air, but by the incredibly tenuous plasma that fills the vast expanses between galaxies. As the radio wave travels for billions of years, it doesn't pass through a perfectly smooth medium. Instead, it encounters a sea of microscopic density fluctuations, tiny ripples and eddies in the ionized gas, like sunlight dappling through a disturbed pool of water. These irregularities act as a diffuse lensing screen, diffracting the wavefront and causing constructive and destructive interference by the time it reaches our telescopes. The pattern of this scintillation is a direct code that astronomers can crack to understand the turbulent nature of the intergalactic medium. When they observe a bright, point-like source like an FRB, they don't see a perfectly steady signal. Instead, they see its intensity modulate rapidly across different radio frequencies and over short periods of time. This creates a specific pattern in the data known as a scintillation arc when analyzed with sophisticated mathematical tools. The shape and curvature of this arc are not random. They hold precise information about the relative distances and the velocity of the scattering material. More importantly, the characteristic scale of the scintillation pattern tells scientists the typical size of the plasma clouds responsible for the effect. It's as if the FRB's radio wave has passed through a sieve, and by studying the pattern of the holes, we can determine the size and distribution of the sieve's mesh. This ability to measure such fine-scale structure is revolutionary. Before FRBs, our view of the intergalactic medium was relatively coarse. We knew it existed from its overall effect on light, but its small-scale structure was largely theoretical. Scintillation studies have revealed that the plasma is far from homogeneous. It is filled with turbulent structures on scales as small as an astronomical unit, the distance from the Earth to the Sun, or even less. These are not solid objects, but rather subtle variations in electron density, the faint echoes of gravitational forces, shock waves from ancient supernova, or outflows from galaxies that have stirred this cosmic soup over eons. By analyzing scintillation patterns from FRBs at different distances and in different directions, astronomers are beginning to map this turbulence spectrum, understanding how energy cascades from large scales down to small ones within the cosmic web. They can ask fundamental questions. Is the intergalactic medium more turbulent near clusters of galaxies? Is it calmer in the great voids? Each new FRB detection adds another day to point to this three-dimensional map of cosmic weather. The implications extend beyond mere mapping. The presence and nature of this small-scale structure have profound consequences for our understanding of cosmic magnetism and the origin of cosmic rays. The turbulent motions in the plasma are likely what amplify and maintain the magnetic fields that permeate intergalactic space, fields that are weak but crucial for shaping the evolution of galaxies. Furthermore, the same turbulent plasma that causes scintillation is also thought to be responsible for scattering and accelerating high-energy particles. By characterizing the turbulence with FRBs, we gain insight into the invisible accelerators that power the cosmic rays constantly bombarding our galaxy. In this role, the fast radio burst transcends its identity as a mysterious explosion and becomes an unparalleled tool. It functions as a nanoscale probe of the largest structures in the universe, using the subtle flicker imposed on its signal by a billion light-year journey to illuminate the hidden turbulence that shapes the cosmos. What appears as noise in the signal is, in fact, a high-resolution message about the fundamental state of the universe's most abundant, yet most elusive component. And here we encounter a profound temporal puzzle that challenges the very timeline of cosmic violence. How old are the objects producing these bursts? Our leading suspect, the magnetar, is typically thought of as a youthful rebel. Born in the fiery cataclysm of a supernova, these ultramagnetic neutron stars are expected to be at their most hyperactive in the immediate aftermath of their birth, perhaps for the first 10,000 years of their existence. Their immense magnetic fields are thought to decay over time, settling down into a more quiescent state. It's a logical story. The most powerful explosions should come from the newest, most energetic engines. This picture fits beautifully with FRBs like 121102, which is located in a dwarf galaxy that is a hotbed of ongoing star formation, a place where new stars, and therefore new magnetars, are being forged all the time. Yet, the cosmic census of FRB host galaxies reveals a far more complicated narrative. We are finding these brilliant flashes in environments that are anything but youthful. Some bursts originate in massive, quiet spiral galaxies like our own Milky Way, places where the era of rampant star formation has largely passed. The most stellar residents in these galactic metropolises are ancient, quiet stars, and the massive stars that could give birth to young magnetars died off billions of years ago. The discovery of a repeater in an ancient globular cluster was the ultimate challenge to the youth paradigm. Globular clusters are retirement homes for stars, containing some of the oldest stellar populations in the universe. How could an environment devoid of young, massive stars host a repeating FRB source? This forces a radical rethinking of the progenitor's life cycle. One compelling solution is that magnetars themselves are not always the short-lived firebrands we imagine. Perhaps they can undergo a kind of cosmic reactivation long after their birth. How could this happen? The answer may lie in the companionship of a binary star system. Imagine an old, dormant neutron star drifting through space. If it has a companion star that begins to shed its outer layers in a stellar wind, or if the neutron star gets close enough to pull material directly from its partner, this infalling matter could work like a cosmic defibrillator. As gas spirals onto the neutron star's surface, it delivers a tremendous amount of energy and angular momentum. This could potentially re-energize the star's magnetic field and spin it up to a ferocious rate, effectively transforming it into a magnetar-like object billions of years after its initial formation. This process, known as accretion-induced collapse or recycling, provides a pathway to creating a powerful FRB engine in an otherwise old and quiet neighborhood. Alternatively, the FRB progenitor might not be a magnetar born from a standard core collapse supernova at all. Another fascinating possibility involves the merger of two white dwarfs. White dwarfs are the Earth-sized embers of Sun-like stars. If two of these stellar corpses spiral together and their combined mass exceeds a critical limit, they can undergo a catastrophic collapse, not into a neutron star, but directly into a highly magnetic neutron star in a single, violent step. This event would produce a magnetar not from a young, massive star, but from the long-dead remnants of older, quieter stars. This formation channel is entirely divorced from recent star formation and could easily occur in an ancient globular cluster or an evolved spiral galaxy, perfectly explaining the presence of an FRB source in a geriatric stellar environment. The age of the progenitor is therefore not a minor detail. It is a fundamental key to classifying the different types of fast radio bursts. It suggests a possible division of labor in the cosmos. The incredibly energetic, one-off bursts might indeed be the death cries of young magnetars or the mergers of young neutron stars, events tied to recent stellar activity. Meanwhile, the repeating bursts with their precise clocks and presence in old galaxies could be the signature of reactivated or alternatively formed magnetars that have found a way to produce their brilliant flashes across cosmic eons. This duality transforms our view from a single mystery to a rich tapestry of stellar evolution, where the universe has multiple ways and multiple timelines for creating the same spectacular signal, ensuring that the night sky is illuminated by these flashes regardless of a galaxy's age or stage of life. This tendency for bursts to arrive in clusters rather than being evenly spaced out reveals a profound truth about the engine driving them. It's a pattern that tells us this is not a simple, steady process like a ticking clock, but something far more analogous to seismic activity here on Earth. When you analyze the waiting time distribution, the statistical pattern of time intervals between one burst and the next, a clear picture emerges. You find that the probability of another burst occurring is highest immediately after a burst has just happened. This likelihood then decays over time, creating those intense clusters of activity followed by stretches of silence. This is the unmistakable signature of a system governed by stress accumulation and release. Think of it like the build-up to an earthquake. Tectonic plates are constantly pushing against each other, but the friction along a fault line locks them in place. Stress builds up relentlessly until it exceeds a critical threshold. At that moment, the fault slips, causing the main shock. But the initial earthquake doesn't resolve all the built-up stress. It redistributes it, triggering a series of aftershocks as the system settles into a new, temporary equilibrium. The clustering of FRBs suggests a very similar physical principle is at work on the surface of a magnetar. The immense magnetic fields of these stars are under unbelievable strain, twisted and sheared by the different rotation rates of the star's solid crust and its superfluid interior. This magnetic stress builds up until it reaches a breaking point, leading to a sudden reconnection of field lines or a fracture in the star's crust, a starquake. This initial cataclysm likely produces the brightest burst in a cluster, but it also destabilizes the surrounding region, triggering a cascade of smaller magnetic readjustments that we observe as the subsequent bursts in the cluster. This model elegantly explains the long quiet periods as well. After a burst cluster, the system has effectively discharged a significant amount of its pent-up stress. It then enters a recharge phase, a quiet period where the magnetic field slowly twists up again or crustal stresses gradually reaccumulate, building toward the next threshold. The duration of this quiet period is not fixed. It depends on the rate at which stress is applied. This could be influenced by factors like the star's spin-down rate, the gradual evolution of its internal magnetic field, or even external influences like the gentle gravitational tug of a companion star. The unpredictable nature of these quiet periods is what makes forecasting the next active window so difficult. We are dealing with a complex system where a small change in the stress loading rate can lead to a large difference in the time between eruptions. An alternative but equally fascinating explanation for the clustering involves an external trigger. Imagine the magnetar surrounded by a debris disk, the remnants of an asteroid or a comet that ventured too close and was torn apart by the star's fierce gravity. In this scenario, the clustering of bursts could be tied to the infall of chunks of this material. A large fragment impacting the magnetar's surface could trigger the initial major burst, while the ensuing cloud of smaller debris, continuing to rain down over hours or days, could be responsible for the subsequent flurry of activity. The quiet period would then correspond to the time it takes for another sizable body to be gravitationally nudged into a destructive orbit. This model adds a layer of cosmic chaos to the process, where the timing of the bursts is not solely determined by the internal dynamics of the star, but also by the random availability of impactors in its immediate environment. The waiting time distribution is therefore a powerful statistical key. By meticulously measuring these patterns across different repeating sources, astronomers can begin to distinguish between these models. Does the distribution follow a specific mathematical form that is characteristic of critical threshold systems, like the Gutenberg-Richter law for earthquakes? Or do the clusters show properties that are more consistent with a random Poisson process that is simply turned on and off, which might favor an external triggering mechanism? Each new cluster of bursts from a repeater provides more data to refine these models, transforming the seemingly random chatter into a detailed stress map of an object under conditions we can scarcely imagine. The clustering is not noise, it is a rhythmic, if complex, drumbeat that allows us to listen in on the building and releasing of titanic forces on a stellar corpse billions of light years away. But our exploration of these cosmic flashes isn't confined to the universe's recent history. It stretches back to its very infancy. This brings us to one of the most thrilling frontiers in FRB research, the search for bursts from the early universe. Astronomers measure cosmic distances using a concept called redshift, denoted by the letter Z. The higher the redshift, the farther away, and thus the older the object is. Our current record holder FRBs have redshifts of around 1 or 2, meaning we see them as they were when the universe was already several billion years old. The new frontier is to push beyond a redshift of 3 to find bursts that erupted when the cosmos was less than 2 billion years old, a mere toddler in cosmic terms. Detecting such an ancient signal would be like receiving a message from the universe's formative years, a time when the first stars and galaxies were just beginning to assemble. The challenge in this search, however, is immense, and it fundamentally changes the nature of the signal we're trying to detect. The expansion of the universe doesn't just stretch distances, it stretches the very light and radio waves traveling through it. This phenomenon, known as cosmological redshift, means that an FRB emitted at a high frequency in the early universe will have its signal shifted to a much lower frequency by the time it reaches us. A burst that might have been born as a brilliant flash at 2 GHz could arrive at our telescopes redshifted down to just 500 MHz or even lower. This pushes the signal directly into the most difficult part of the radio spectrum to observe, where interference from Earth is rampant and where the effects of scattering and absorption by interstellar plasma are most severe. Furthermore, the journey across a younger, denser universe results in an even greater dispersion measure. The signal is not only stretched in frequency, but also smeared out over a longer period of time, making it fainter and more challenging to distinguish from the background radio static. Finding these ancient bursts requires telescopes with exceptional sensitivity at low frequencies and sophisticated signal processing algorithms capable of searching for these heavily distorted whispers. Yet, the scientific payoff for overcoming these challenges would be nothing short of revolutionary. An FRB detected from the epoch of reionization would become the most powerful probe ever devised for studying that pivotal chapter in cosmic history. The epoch of reionization was the universe's great transformation. After the hot, dense conditions of the Big Bang cooled, the universe entered a period known as the Dark Ages, filled with a fog of neutral hydrogen gas. Then, roughly a few 100 million years later, the first stars and galaxies ignited. Their intense ultraviolet radiation began to strip electrons from the hydrogen atoms, reionizing the cosmic fog and clearing the way for light to travel freely. Understanding exactly how and when this process unfolded is one of the major goals of modern cosmology. An FRB from this era would act as a brilliant, momentary backlight. As its radio waves traveled through the partly neutral, partly ionized intergalactic medium of the young universe, they would carry an exact imprint of the ionization state along its path. By meticulously analyzing the dispersion measure and how the signal is shaped by this primordial plasma, astronomers could measure the density and the fraction of neutral hydrogen at that specific time with unparalleled precision. It would be like using a flashbulb to take a snapshot of the cosmic fog as it was lifting, providing a direct measurement of a key transition that shaped the entire future evolution of the cosmos. The hunt for these high redshift FRBs is already underway, driven by next-generation telescopes with wider fields of view and enhanced low-frequency capabilities. Each new survey pushes the limits further, scanning the skies for that one-in-a-million burst that carries the indelible stamp of the ancient universe. A successful detection would do more than just break a distance record. It would open an entirely new window onto the conditions that existed when the first structures were forming. It would allow us to test our models of the earliest generations of stars and the objects that could have produced such immense energy so soon after the Big Bang. Were the first magnetars even more powerful than their modern counterparts? The search for FRBs in the early universe is therefore a quest to connect the violent phenomena we see today directly to the primordial events that set the stage for everything that followed, turning these fleeting millisecond signals into time machines that can transport us back to the dawn of cosmic time. While the magnetar model provides a compelling framework, the sheer diversity of fast radio bursts has pushed theorists to dream up even more specific and intricate scenarios to explain the most complex repeaters. One of the most vividly named and detailed of these is the Dragon model. Picture this: a newborn neutron star, a magnetar, still blazing with the heat of its creation, is not floating alone in space. Instead, it's shrouded by a dense, orbiting disk of debris, the leftover ashes from the supernova explosion that gave it birth. This is the Dragon's lair. The neutron star itself is the beast, possessing an immensely powerful and dynamic magnetic field. In this model, the star doesn't produce the radio burst directly. Instead, it periodically unleashes a flare, a sudden, violent eruption of energy, perhaps in the form of X-rays or a wind of particles. This flare then slams into the surrounding debris disk. The interaction is catastrophic. The immense energy of the flare ionizes and heats a portion of the disk to incredible temperatures, causing it to light up brilliantly and emit a focused beam of coherent radio waves, the fast radio burst we detect. The Dragon's breath, in this analogy, is the radio flash ignited as the star's fury strikes the surrounding material. What makes the Dragon model so attractive is its ability to explain several puzzling features at once. The surrounding disk naturally accounts for the extreme Faraday rotation and scattering seen in some repeaters, as the radio waves must escape a dense, magnetized environment. It also provides a ready-made reason for repetition. The magnetar can flare many times, each flare interacting with the disk to produce a new burst. The model can even accommodate the strange downward drifting chirps if the emitting region within the disk is moving rapidly, causing a change in frequency over the brief duration of the burst. It's a comprehensive picture that ties the central engine to a persistent and complex local environment, turning the entire system into a sophisticated cosmic generator. Yet the dragon is far from the only mythical beast in this theoretical zoo. Another compelling idea is the cosmic comb model. This framework imagines a different kind of binary dance. In this case, a rapidly spinning neutron star, like a pulsar, emits a steady, powerful wind of charged particles. This wind then sweeps through a dense, stationary cloud of plasma that lies along its path, perhaps a cloud ejected from a companion star. As the pulsar wind passes through this cloud, it excites the plasma within, causing it to emit coherent radio waves in a series of rapid pulses. The regular spin of the pulsar effectively combs through the cloud, producing a sequence of bursts that could explain the precise periodicity seen in some sources. Here, the engine is the interaction between two distinct components, a pulsar's wind and a plasma cloud, rather than a single object undergoing internal convulsions. Other models focus on the dynamics of shock waves. Imagine a single, sudden explosion, a starquake, or a magnetic reconnection event that sends a blast wave racing outward from a neutron star. This shock wave then plows into the surrounding medium, which could be the neutron star's own pre-existing wind or a shell of previously ejected material. As the shock propagates, it accelerates electrons to high energies, and these electrons then produce coherent radio emission. The complex morphology of a burst, its jagged profile or multiple sub-pulses, could then be mapped to the shock wave interacting with a clumpy, uneven environment. Different densities of material would cause brighter or dimmer flashes, creating the intricate structure we observe. This model elegantly explains why some bursts look so messy. They are a direct recording of a chaotic interaction happening in real time. The existence of these diverse and highly detailed models is a testament to the complexity of the problem. No single framework has yet achieved the status of a universal theory. The dragon model beautifully explains repeaters embedded in dense environments, but might struggle with bursts that show very little scattering. The cosmic comb requires a very specific binary configuration that may not be common enough to account for the vast number of FRBs we infer. Shock wave models are excellent for one-off cataclysmic events, but need additional mechanisms to account for repetition. What this tells us is that the universe is likely employing more than one method to create these brilliant flashes. The term fast radio burst may not describe a single type of event, but rather a final, common signal produced by several different cosmic processes. A spectacular radio scream that can be uttered by a dragon in its lair, a pulsar combing a cosmic cloud, or a shock wave ripping through the fabric of space. This vibrant theoretical battleground is not a sign of failure, but a sign of a rich, active field of science, where each new observation helps to refine our imagination of the possible. Yet, even after accounting for the main dispersion effect, a subtle and more elusive fingerprint is sometimes left on the signal, one that requires exquisitely precise measurements to detect. This is the mystery of frequency-dependent dispersion measure variations. You'll recall that the standard dispersion measure is the result of radio waves traveling through a cold, classical plasma, a simple soup of free electrons. In this model, the delay between high and low frequencies follows a very specific, predictable law. The delay is exactly proportional to the inverse square of the frequency. This is a fundamental rule for how light behaves in such a plasma, and for most astronomical purposes it holds perfectly true. But for a handful of repeating fast radio bursts, when astronomers perform measurements of astonishing precision, they find a tiny, additional deviation from this perfect law. The dispersion measure itself appears to change ever so slightly depending on which frequency you measure it at. It's as if the universe is adding a faint, complex harmony to the simple, predictable chord of plasma dispersion. These minuscule deviations are far more than just a technical curiosity. They are a potential window into physics operating under conditions so extreme they defy our everyday experience. One compelling explanation ventures into the realm of quantum electrodynamics. the plasma surrounding the FRB source might not be a simple, cold sea of electrons. Instead, it could be what's known as a pair plasma, a seething environment filled with equal numbers of electrons and their antimatter counterparts, positrons. This kind of plasma can be created in the immense magnetic fields near a magnetar, where the energy is so high that particle-antiparticle pairs are spontaneously created from the vacuum. In a pair plasma, the quantum nature of the particles and their interactions with the intense magnetic field can alter the way radio waves propagate in subtle ways, introducing a small correction to the standard dispersion relation that depends on the frequency. Detecting this effect would be like finding the signature of antimatter in the heart of a cosmic storm, confirming that the environment around these engines is a laboratory for some of the most exotic physics in the universe. Another possibility brings us back to the immense winds that might be blowing from the central neutron star. Imagine a dense, relativistic wind of particles streaming outward at nearly the speed of light. If the FRB's radio waves must travel through this wind, they could interact with it in a way that mimics a change in the dispersion measure. The wind is not a static medium. Its density and velocity might change with distance from the source. Different frequency components of the radio burst, due to their different wavelengths, could effectively sample slightly different parts of this structured, flowing wind, leading to the observed frequency-dependent variations. This would turn the signal into a sophisticated probe of the wind's structure, allowing us to map its density and speed gradients right near the central engine. Unraveling this delicate mystery is a task for the most advanced radio telescopes and data analysis techniques. It requires comparing the arrival times of bursts across an extremely wide band of frequencies with nanosecond precision, a feat that pushes the limits of our technology. But the payoff would be immense. Confirming and interpreting these tiny deviations would give us a direct diagnostic of the plasma conditions in the most immediate vicinity of the FRB source. Is it a cold, classical plasma or a hot, quantum pair plasma? Is the environment static or dominated by a relativistic wind? Each type of plasma leaves a distinct, frequency-dependent fingerprint on the passing radio waves. By reading this subtle code, we could move from simply knowing that a magnetar is there to understanding the precise quantum electrodynamic state of its atmosphere, peering directly into the crucible where magnetic and particle energies reach levels unattainable in any laboratory on Earth. This finest of measurements represents a new frontier in high-energy astrophysics, where the fleeting whispers of distant cosmic explosions allow us to test the fundamental laws of physics in their most extreme limits. While we have pieced together a remarkable story from the few hundred fast radio bursts detected so far, we are truly on the cusp of a revolution that will transform this field from a niche mystery into a mainstream branch of astronomy. This coming leap is powered by a new generation of radio telescopes, instruments so powerful they will turn the occasional cosmic flash into a constant floodlit spectacle. Leading this charge are projects like the Deep Synoptic Array, already coming online, and the Colossal Square Kilometer Array, a truly international endeavor that will be the largest scientific instrument ever built. Their power lies in a combination of two factors that have traditionally been a trade-off: immense sensitivity and an incredibly wide field of view. Think of it like this. Current telescopes are like looking at the sky through a narrow but powerful telescope. You see a tiny patch in great detail, but you're likely to miss the fleeting flash that happens just outside your view. The new generation, however, is like having a camera with a fish-eye lens that can capture the entire sky in ultra-high definition all at once. The Deep Synoptic Array, with its 210 dishes working in concert, can scan vast swaths of the heavens continuously. But it is the Square Kilometer Array that represents the ultimate game changer. When its thousands of antennas spread across South Africa and Australia are fully operational, it will be so sensitive that it could detect an airport radar on a planet tens of light years away. More importantly for FRB science, it will be able to discover and pinpoint the location of not just a few bursts per month, but potentially tens of thousands every single year. This deluge of data will allow us to move from studying individual curiosities to understanding FRBs as a population, much like a biologist who transitions from examining a few rare butterflies to having a complete catalog of every insect in a rainforest. With thousands of well-localized bursts, we can finally perform statistical studies of unprecedented power. Are all repeating FRBs found in dwarf galaxies? Do one-off bursts always come from more massive, quiet galaxies, or is the picture far more mixed? This volume of data will allow us to identify subtle subclasses of bursts that are invisible to us now. We might discover that what we currently call repeaters actually include several distinct families of objects, each with its own unique fingerprint in terms of energy, polarization, and host environment. The repeater versus one-off dichotomy could be clarified or even completely upended, revealing a continuum of behavior dictated by the age, magnetic field strength, or environment of the progenitor. Beyond simply classifying the bursts themselves, this flood of detections will transform FRBs into a routine, high-precision tool for cosmology. Each localized burst acts as a core sample of the cosmic web. With tens of thousands of these core samples taken from galaxies at all different distances and in all directions, we will be able to construct a three-dimensional map of the distribution of ordinary matter in the universe with finer detail than ever before. This will not only solve the missing baryon problem definitively, but also allow us to trace the evolution of the cosmic web over billions of years. We could potentially detect the gravitational influence of dark matter on the large-scale structure by seeing how it subtly warps the paths these radio waves take. Furthermore, by comparing the dispersion measures of very distant FRBs with those from closer ones, we can measure the expansion history of the universe itself, providing an independent check on measurements from other methods like supernova. In the hands of these new telescopes, fast radio bursts will cease to be just mysterious explosions and will become the standard candles and cosmic probes of the 21st century, illuminating the darkest and most elusive components of our universe with their brilliant, fleeting light. But for all the spectacular fireworks we've managed to catalog, we have to confront a sobering possibility. Our current view of the fast radio burst universe is like looking at a city at night and only seeing the occasional spotlight, completely missing the vast sea of dimmer streetlights that must also exist. This is the mystery of the missing low-energy bursts. Our telescopes, as incredible as they are, have a fundamental sensitivity threshold. They are designed to catch the brightest, most attention-grabbing events, the cosmic shout that can be heard from billions of light-years away. This creates a powerful observational bias, meaning we have an incomplete and potentially skewed picture of what's really happening out there. The logic is compelling. In every other category of cosmic explosion we've ever studied, from supernova to gamma-ray bursts, the rule holds true. Low-energy events are far more common than high-energy ones. It's the same principle as an earthquake scale. There are countless tiny tremors for every single massive, civilization-rattling quake. There is no reason to believe fast radio bursts would be any different. In fact, the sheer number of extremely energetic FRBs we do detect, even with our limited view, strongly implies that a truly immense population of fainter, weaker bursts must be occurring constantly, a faint cosmic static that our current equipment simply isn't sensitive enough to pick up. These would be the bursts from closer galaxies or from less violent eruptions on more distant magnetars, flashes that don't quite cross the brightness threshold needed to register above the background radio noise of the universe. Uncovering this hidden population is one of the most important goals for the next generation of telescopes, because what these low-energy bursts could tell us is profound. Their discovery would allow us to finally construct a complete luminosity function for FRBs, a chart showing how many bursts occur at each energy level. This is the master key to understanding the life cycle of these engines. Are we seeing a smooth, continuous distribution from the faintest whispers to the most powerful roars? That would suggest a single class of object, like a magnetar, that can produce outbursts across a wide range of energies, perhaps depending on the size of the starquake or the intensity of the magnetic reconnection event. The relative commonness of the faint bursts would tell us about the typical, everyday activity level of these objects, while the rare giants would represent their absolute maximum output. Alternatively, the luminosity function might reveal a break or a bimodal distribution, a clear gap that separates the low-energy bursts from the high-energy ones. This would be a bombshell discovery, hinting that we are actually dealing with two distinct populations of progenitors. Perhaps the faint, frequent bursts are caused by smaller, more common events, like minor crustal adjustments on nearby, older neutron stars. Meanwhile, the colossal, galaxy-outshining bursts could be the exclusive domain of the youngest, most hyper-magnetic magnetars in the universe, or from entirely different cataclysms like neutron star mergers. Finding this divide would force us to split the FRB phenomenon into separate categories, each with its own unique origin story and cosmic role. The hunt for these faint signals is already pushing technology to its limits. It requires radio telescopes with unprecedented sensitivity and surveys that can stare at the same patch of sky for thousands of hours, integrating the faintest of signals out of the noise. The hope is to catch bursts from magnetars within our own local group of galaxies, events that would be thousands of times fainter than the extragalactic giants, but would provide an incredibly detailed, close-up view of the engine in action. Discovering this hidden chorus of weak FRBs would complete our census of cosmic violence, revealing the full spectrum of activity from the most extreme objects in the universe, and finally answering the question of whether we are listening to a single voice shouting at different volumes or an entire choir of different singers, each with their own part to play in the cosmic symphony. To truly appreciate the magnetar's role in the fast radio burst mystery, we need to look at its most dramatic performances right here in our own cosmic neighborhood. This brings us to a class of objects that have been captivating high-energy astronomers for decades, soft gamma repeaters, or SGRs. These are not distant theoretical suspects. They are confirmed magnetars within our own Milky Way galaxy, and they provide a living laboratory for the kind of violence we suspect is powering FRBs. As their name implies, soft gamma repeaters are known for their behavior. They unleash intense, repeating flares of X-rays and soft gamma rays. These are not the steady, ticking signals of a pulsar. They are erratic, powerful outbursts with occasional giant flares so bright they can temporarily outshine the entire galaxy in high-energy light. The parallels to FRBs are immediately striking. Both phenomena involve a compact object erupting in brief, incredibly energetic bursts. Both show repetition, with periods of frantic activity followed by long stretches of quiescence. And both have a giant flare category for SGRs. It's an event like the legendary flare from SGR 18026 in 1998. And for FRBs, it's the most energetic one-off bursts that outshine galaxies. Yet, for all these similarities, there is one glaring and crucial difference: the radio emission. The vast majority of flares from our local soft gamma repeaters are prolific in X-rays and gamma rays, but they are notoriously quiet in the radio part of the spectrum. This creates a fascinating puzzle. If a magnetar like SGR 1935 plus 2154 can produce an FRB, as we witnessed in 2020, why don't all magnetar flares do the same? Why is the brilliant radio flash the exception rather than the rule for the magnetars we can study up close? This discrepancy is the key to understanding what special conditions are required to turn a high-energy magnetar flare into a full-fledged fast radio burst. The answer likely lies in a combination of three factors: energy, geometry, and environment. First, let's consider the energy scale. The radio burst from our galactic magnetar in 2020 was thousands of times less energetic than the most powerful extragalactic FRBs. This suggests there might be a threshold effect. Perhaps only the most colossal magnetar eruptions, those that release energy on a truly superlative scale, are capable of producing the conditions necessary for the coherent radio emission we see from across the universe. In this view, the flares we typically see from nearby SGRs are simply not powerful enough. They are impressive by our standards, but they might be the equivalent of a minor spark compared to the stellar scale inferno required to launch a detectable radio signal across intergalactic space. The extragalactic FRBs we detect would then be the absolute upper limit of magnetar activity, the rare, super-powerful events that push the physics into a new regime. The second piece of the puzzle is geometry, specifically the orientation of the magnetic field and the beaming of the emission. Radio waves from a magnetar are almost certainly not emitted in all directions like a bare light bulb. Instead, they are beamed, focused into a narrow jet, much like the lighthouse beam from a pulsar. Whether we see a brilliant radio flash depends critically on whether that beam is pointed directly at Earth. An SGR might experience a giant flare, but if its radio jet is pointed away from us, we would only detect the X-rays and gamma rays, which might be emitted in a wider cone. This could explain why bright radio bursts seem so rare from our local magnetars. We are simply not in the firing line for their radio beams most of the time. The situation is different for an extragalactic magnetar, because there are billions of galaxies, each potentially hosting multiple magnetars. The chance that one of their beams will sweep across our planet is much higher, making the detection of these focused radio flashes a more common occurrence from a cosmic perspective. Finally, and perhaps most importantly, is the role of the environment. This is where the connection to soft gamma repeaters becomes particularly insightful. Many of the magnetars in our galaxy are relatively isolated, old objects whose violent birth clouds have long since dissipated. They are firing their flares into a relatively clean, thin interstellar medium. Now contrast this with a young magnetar like the one thought to power FRB 121102, which is likely still embedded in the dense, magnetized nebula of its own supernova remnant. This surrounding material could be absolutely essential for producing the bright radio emission. When a magnetar flare erupts, it slams into this dense nebula. The interaction between the flare's energy and this thick, surrounding plasma could be what actually generates the coherent radio waves through processes like a synchrotron maser. In this scenario, the radio burst isn't created directly at the star's surface, but in the shock front where the flare collides with the nebula. If this is correct, then a magnetar without a dense environment might still produce a spectacular X-ray and gamma-ray flare, but it would lack the screen upon which to project its radio brilliance. The presence of a dense, circumstellar environment could be the decisive factor that transforms a high-energy outburst into a multi-wavelength cosmic firework, providing the missing link between the relatively radio-quiet SGRs in our galaxy and the radio-loud FRBs we see from afar. This would mean that when we detect a fast radio burst, we are not just seeing a magnetar, but a magnetar at a very specific, youthful stage of its life, still cocooned within the turbulent aftermath of its own violent birth. But as we zoom in even closer, dissecting these bursts with the equivalent of a cosmic microscope, we uncover a level of detail that speaks to the very microphysics of the explosion. This brings us to a subtle yet profoundly revealing mystery, the phenomenon of bandwidth narrowing within subbursts. We've already seen how some complex FRBs break apart into a cascade of individual subpulses, each with its own downward drifting chirp. Yet when astronomers analyze these subbursts with extreme precision, they notice something even more specific. Each individual subpulse often occupies a much narrower slice of the radio spectrum than the overall burst envelope. Imagine a brilliant flash of white light that, when passed through a prism, doesn't just create a smooth rainbow, but instead resolves into a series of distinct, sharply defined colored lines. This is the essence of bandwidth narrowing. It suggests that the engine isn't just firing off a single, broadband blast of radio noise. It's producing a rapid sequence of highly tuned, almost monochromatic emissions, each one a precise note in a fleeting cosmic chord. This fine structure is a treasure trove of information because it points directly to the specific conditions within the emission region. For a radio signal to be confined to a narrow band of frequencies, it must be generated within an environment that has very particular, well-defined properties. Think of it like a musical instrument. A large pipe organ can produce a wide range of notes because it has pipes of many different lengths and shapes. But a single, perfectly tuned flute can only produce sound within a much narrower acoustic range. In the same way, a narrow band subburst suggests that the radio waves are being produced in a highly localized and constrained volume of plasma. The width of that frequency band is like a thermostat reading for the local environment. It tells us about the temperature, density, and magnetic field strength in that exact spot where the emission is happening. What could create such localized conditions? One compelling idea points to the fundamental architecture of a magnetar's magnetic field. These fields are not simple, smooth dipoles. They are likely a complex tangle of individual magnetic flux tubes, like a bundle of immensely powerful, twisted rubber bands. Each subburst, with its narrow bandwidth, could be the signature of a single, specific magnetic field line suddenly releasing its pent-up energy. As stresses build up, a field line might snap and reconnect, accelerating a bunch of electrons that then emit coherent radiation as they spiral along that particular field line's unique curvature. The narrow bandwidth would then reflect the homogeneous conditions along that single, well-defined magnetic highway. The next subburst would be generated on a different field line with slightly different properties, accounting for the slight variation in frequency that creates the overall downward drift. Alternatively, this could be the signature of a propagating shock wave. Imagine a single explosive event sending a blast wave racing through a clumpy, uneven medium. As this shock front encounters a dense knot of plasma, it compresses and heats it, triggering a flash of coherent radio emission at a frequency determined by the precise density and magnetic field of that specific knot. The shock then moves on, and a millisecond later, it hits another clump with slightly different properties, producing the next subburst at a different frequency. In this scenario, the narrow bandwidth of each subpulse is a direct measurement of the local conditions within each individual cloud of material being shocked. The entire sequence of subbursts then becomes a real-time sonar map, tracing the shock wave's path through a turbulent and structured environment, revealing the microscopic texture of the space surrounding the central engine. This level of detail transforms each complex FRB from a simple flash into a high-resolution diagnostic, allowing us to probe the heart of the explosion on scales smaller than our own planet, from an impossible distance across the universe. Now, if we want to understand the very shape of the explosion itself, we need to move from asking what powers these bursts to asking how the brilliant radio flash is actually shaped and launched into space. This brings us to a fascinating theoretical debate over the geometry of the emission, a clash of models that pits two very different visions of the cosmic engine against each other. On one side, we have the classic and intuitive lighthouse model, and on the other, a more complex but compelling idea known as the crater model. The lighthouse model is an elegant concept borrowed directly from our understanding of pulsars. Imagine a neutron star spinning rapidly, perhaps dozens or even hundreds of times per second. Its immensely powerful magnetic field is not aligned with its rotation axis. Instead, the magnetic poles are offset, and from these poles, narrow beams of radio emission are launched, like two powerful searchlights fixed to a rotating platform. As the star spins, these beams sweep across the cosmos. From our distant vantage point, we only see a brilliant flash of radio waves when one of these beams momentarily points directly at Earth. This model beautifully explains the strict periodicity seen in some repeaters. The 16-day cycle of FRB 180916, for instance, could be the orbital period of the neutron star, while the active window within that cycle could be caused by a slower wobble or precession of the star's spin axis, causing the beam to sweep across us for a few days at a time. In this picture, the burst morphology, the presence of multiple subpulses within a single burst, could be explained by multiple active regions on the star's surface, each creating its own beam that sweeps past us in quick succession as the star rotates. However, the lighthouse model faces some significant challenges. The biggest is the incredible brightness of these bursts. For a rotating beam to appear so brilliant, the emitting region must be extremely efficient, focusing an immense amount of energy into a very narrow cone. Furthermore, the rapid, complex structure of some bursts, with their jagged profiles and intricate frequency drifts, is difficult to reconcile with a simple, cleanly rotating beam. This has led theorists to propose an alternative geometry, the crater model. In this scenario, the emission doesn't come from a sweeping beam at all. Instead, it originates from a fixed point on the neutron star's surface, a crater of intense magnetic activity. Picture a single, powerful flare erupting from a specific magnetic hotspot. The radio waves themselves are initially emitted in a wide angle, but before they can escape, they must pass through a dense, magnetized plasma that hovers just above the star's surface. This plasma can act as a powerful lens, bending and focusing the radio waves into a narrow beam that shoots out into space. This process, known as plasma lensing, is like the lens in a lighthouse, but it's not attached to a rotating platform. It's a fixed lens focusing the light from a fixed flashbulb. Distinguishing between these two models becomes a detective game of examining the subtle fingerprints left on the signal. One of the most powerful diagnostics is the behavior of the radio wave's polarization. In the lighthouse model, as the beam sweeps across our line of sight, the angle of linear polarization should smoothly and predictably rotate over the duration of the burst. This sweeping polarization angle is a hallmark of a rotating magnetic field structure and is commonly seen in pulsars. If astronomers could measure this smooth swing in an FRB, it would be strong evidence for a rotating lighthouse beam. The crater model, by contrast, predicts a much more stable polarization angle. Since the emission comes from a fixed location with a fixed magnetic field geometry, the polarization direction should remain constant throughout the burst. The complex variations we sometimes see would then have to be explained by intricate plasma lensing effects distorting the signal as it escapes. The burst morphology itself provides another clue. A lighthouse beam sweeping across a turbulent, structured environment could produce a burst with a single, smooth peak. But the crater model might be better at explaining bursts with extremely complex, multi-peaked structures. In this picture, the single flare from the crater interacts with a clumpy, uneven plasma lens. Different parts of the wavefront are focused and defocused at slightly different times, creating a burst that looks like a series of sharp spikes and dips, a direct recording of the lens's imperfections. The downward drifting chirp of sub-bursts could be naturally explained by the emitting plasma rising or cooling within the fixed crater, causing the emission frequency to change over time. Ultimately, these two models may not be mutually exclusive. It's possible that a rotating neutron star has multiple magnetic craters on its surface. The overall periodicity would be governed by the star's spin, but the fine structure of each individual burst would be determined by the complex physics of plasma lensing at each crater. The challenge for observers is to gather enough high-quality data on the polarization and microstructure of many bursts to see which pattern holds true. Are the polarization angles consistently swinging, or are they mostly stable? The answer will tell us if we are looking at the stately sweep of a cosmic lighthouse or the brilliant, focused flash from a fixed magnetic crater, helping us to visualize the precise architecture of one of the most powerful engines in the universe. But just as we begin to chart the active lives of these cosmic engines, a deeper question arises about their ultimate destiny. If a repeating fast radio burst source can flare up with such violence for decades, what does its future hold across the grand sweep of cosmic time? The key to unlocking this mystery lies in the very power source of a magnetar, its unimaginably strong magnetic field. This field is not a perpetual, infinite resource. It is a vast reservoir of stored energy that slowly, inevitably decays over time. The primary mechanism for this decay is thought to be a process called ambipolar diffusion, where the magnetic field gradually dissipates its energy by heating the neutron star's interior and driving a gentle wind of particles from its surface. This isn't a rapid collapse, it's a slow leak from a cosmic battery that might have a half-life of thousands of years. As this fundamental power source dwindles, the entire character of the magnetar's activity must transform. We can imagine a life cycle for a repeating FRB source unfolding in distinct chapters. In its fiery youth, shortly after the supernova that birthed it, the magnetar possesses its maximum magnetic strength and is likely embedded in a dense nebula of its own ejecta. This is its hyperactive phase, a period of frequent and potentially extremely energetic bursts, much like the storm we witnessed from FRB 2020-1124A. The intense magnetic stresses, combined with interactions with the surrounding debris, create a perfect storm for prolific radio emission. As the millennia pass, the magnetic field weakens, and the birth nebula expands and dissipates into the interstellar medium. The star's rotation also slows down, reducing another source of stress. In this adolescent or adult phase, the bursts may become less frequent and less energetic, settling into a more predictable, periodic pattern governed by its binary orbit or its own precession, like FRB 1809-16. The engine is still powerful, but it has settled down from its chaotic infancy. The final chapter in this life story is dormancy. After tens of thousands of years, the magnetic field will have decayed to a level comparable to that of an ordinary, non-magnetic pulsar. The stresses that once caused catastrophic starquakes and magnetic reconnections will have faded away. The object may continue to spin down, emitting a steady wind of radio waves like a typical pulsar, but the brilliant, coherent flashes that defined its youth will cease entirely. It becomes a quiet stellar corpse, its days of spectacular violence a distant memory. This evolutionary sequence suggests a profound link between the type of FRB we observe and the age of its source. The incredibly active, heavily scattered repeaters might be the toddlers of the magnetar world, while the periodic, cleaner sources could be the mature adults. The one-off bursts, then, could represent either the spectacular, self-destructing death of a magnetar or the singular birth cry of a new one, events that bookend this long life cycle. Understanding this timeline is not just an academic exercise, it is crucial for solving the cosmic census of FRBs. If the active bursting phase is relatively short, say 10,000 years, then at any given moment, only a small fraction of the magnetars in a galaxy will be capable of producing FRBs. This would mean that for every brilliant repeater we see, there must be a vast population of dormant or deceased magnetars that we do not see. Conversely, if the bursting phase can be sustained for hundreds of thousands of years through processes like accretion from a companion star, then the population of active FRB sources could be much larger. By measuring the burst rates from galaxies of different ages and comparing them to models of stellar evolution and magnetic field decay, astronomers can work backwards to determine the typical active lifetime of these engines. This allows us to connect the fleeting millisecond flashes we detect today to the grand billion-year life stories of the universe's most magnetic stars, transforming each burst from a single day to point into a timestamp in the epic evolution of cosmic violence. And so we arrive at the final and perhaps most profound mystery that ties all the others together. After exploring 49 distinct puzzles from the whispering echoes of the early universe to the intricate clockwork of repeating bursts, we are left standing before the ultimate cosmic question: can there ever be a single, unified theory of fast radio bursts? The evidence, as we've seen, is compellingly contradictory. On one hand, the detection of a burst from a known magnetar in our own galaxy feels like a triumphant endpoint, a smoking gun that seems to close the case for at least a major class of these events. It provides a beautiful, elegant framework. Hypermagnetic neutron stars, through starquakes or magnetic reconnection, can indeed produce the brilliant, coherent radio flashes we detect from across the cosmos. It's a powerful narrative that brings a satisfying sense of order to the chaos. Yet, the universe consistently refuses to be shoehorned into a single, neat category. For every piece of evidence that supports a unified magnetar theory, there is an outlier that defiantly challenges it. How does the same basic engine account for the staggering difference between a sporadically repeating source like 121102, a periodically ticking clock like 180916, and a completely silent, one-off event that leaves no trace? Why do we find these bursts in the frantic, star-forming dwarf galaxies, the quiet, elderly spiral galaxies, and even the ancient stellar graveyards of globular clusters? The sheer range of energies is perhaps the most telling clue, spanning a factor of millions from the faintest detected bursts to the monsters that can outshine galaxies. This isn't just a matter of turning the volume knob up or down on the same stereo. It suggests fundamentally different amplifiers at work. This forces us to confront two radically different possibilities for the future of FRB science. The first is the unified magnetar scenario. In this view, magnetars are not all identical. They are a diverse family with a wide spectrum of magnetic field strengths, ages, spin rates, and most importantly, environments. A magnetar's behavior could be entirely dictated by its life story. A newborn magnetar, swaddled in a dense supernova remnant, might produce highly scattered, energetic bursts with a persistent radio source. A middle-aged magnetar in a binary system might settle into a precise, periodic pattern dictated by its orbital dance. And an old, isolated magnetar whose field has decayed might only rarely build up enough stress for one final, cataclysmic blast, a one-off burst signaling its impending quietus. In this unified picture, fast radio burst is simply the name we give to the radio signature of a magnetar passing through different phases of its long and violent life. The diversity we see is not a problem to be solved, but the expected result of applying the same fundamental physics across a vast range of initial conditions. The competing and equally valid possibility is the multiple origins hypothesis. This is the idea that we have been fooled by a cosmic coincidence. The term fast radio burst may be a catch-all label we've applied to the final, similar-looking radio scream produced by several completely different cosmic catastrophes. In this more complex universe, repeating FRBs are indeed the work of magnetars, but the single, immensely powerful one-off bursts could be the signature of an entirely separate class of event: the collapse of an overly massive neutron star into a black hole, the merger of two neutron stars, or even the annihilation of a primordial black hole. The dark FRBs, those with no visible host, might be produced by hypervelocity neutron stars ejected from their galaxies entirely, wandering the void. This scenario acknowledges that the universe is creative and that it may have discovered multiple pathways to generate a millisecond flash of radio waves. The path to resolving this grandest of mysteries will not be found in a single, definitive observation, but in the painstaking statistical work that lies ahead. The next generation of telescopes, like the Square Kilometre Array, will not just find more bursts, they will map the entire population. By building a vast catalogue of thousands of events with known energies, host galaxies, and repetition patterns, astronomers will be able to perform a cosmic taxonomy. They will look for clear groupings in the data. Do all repeating bursts share a common energy limit? Do one-offs exclusively occur in certain types of galaxies? If the properties form a smooth, continuous distribution, it will powerfully support the unified magnetar idea. But if the data reveals distinct, separate clusters, a family of repeaters here, a family of one-offs there, with a clear gap between them, it will be compelling evidence for multiple progenitors. Ultimately, the greatest mystery of fast radio bursts may not be about the bursts themselves, but about our place in understanding the cosmos. They have humbled us, revealing that even in the silent gaps between the stars, the universe is crackling with a violence and complexity we are only beginning to perceive. Whether the answer is a single, elegant universal engine or a rich tapestry of different cosmic fireworks, the journey to find out will undoubtedly lead us to new physics and a deeper appreciation for the dynamic, explosive universe we call home. The story of FRBs is far from over. In many ways, with the tools now on the horizon, it is just beginning. And so our journey through these 50 mysteries brings us to a remarkable realization. What began as a single, baffling blip in archival data has blossomed into an entire field of astronomy, a journey that has taken us from profound skepticism to the confident use of these flashes as tools to weigh the cosmos itself. We have traveled from the chaotic hearts of newborn magnetars to the silent voids between galaxies, using each millisecond burst as a key to unlock a different secret. Fast radio bursts are no longer just enigmatic cosmic explosions to be solved. They have become some of the most powerful probes we have for studying the universe's darkest secrets, from the invisible web of missing matter to the turbulent magnetic fields that shape the evolution of galaxies. They force us to confront physics at its most extreme, in environments where matter is crushed to impossible densities and magnetic fields can tear atoms apart. The pace of discovery has been nothing short of breathtaking. In less than 2 decades, we have moved from debating whether these signals were even real to pinpointing their homes in distant galaxies, catching them in the act within our own Milky Way, and using their dispersed echoes to take a core sample of the cosmos. This rapid progress is a testament to human curiosity and technological ingenuity, a global collaboration of telescopes and theorists working in concert to decipher the universe's most fleeting messages. And this is merely the beginning. The next chapter, driven by observatories like the Deep Synoptic Array and the monumental Square Kilometre Array, promises to transform this field from a study of individual curiosities into a vast statistical science. We will move from examining a few rare fireflies to seeing the entire night sky illuminated by their light, discovering tens of thousands of bursts and finally constructing a complete picture of their life and times. This story is a powerful reminder that our understanding of the universe is not a static monument, but a living, breathing, and constantly evolving conversation with nature. Fast radio bursts have humbled us, showing how much we still have to learn, but they have also empowered us, providing a new lens through which to see the invisible architecture of reality. The greatest takeaway is to embrace the mystery itself, to stay curious, to follow the latest findings as they unfold, and to appreciate that we are living in a golden age of discovery, where every new flash from the dark holds the potential to rewrite our textbooks and reshape our place in the cosmos. The universe is speaking to us in a language of brilliant millisecond radio whispers, and we are only just learning how to listen. So as we stand at the edge of this cosmic frontier with 50 mysteries laid out before us, I have to turn the question over to you. Which of these enigmas captures your imagination the most? Is it the clockwork precision of the periodic repeaters, the haunting silence of the dark bursts with no visible home, or the sheer, impossible energy that defies our understanding of physics. The comment section below is your launchpad for cosmic speculation. Share your own theories, your favorite mysteries, and let's continue this conversation together. This is a living science, and your curiosity is a part of it. To make sure you're with us for the next big breakthrough, when a new discovery rewrites the textbooks, be sure to subscribe to the channel and ring the notification bell. The story of fast radio bursts is unfolding in real time, and you won't want to miss a single chapter as we piece this puzzle together. And as we sign off, carry this final thought with you. Every one of those millisecond flashes, every burst of radio waves that has journeyed for billions of years to gently brush against our telescopes is more than just data. It is a direct message from the cosmos, a piece of a grand puzzle that spans the entire history of the universe. Each one is a reminder that we live in a reality of staggering scale and dynamism,